Our gentle journey begins with the simple act of slowing down, of letting the mind drift toward a time so far in the past that it feels almost outside of imagination. We are speaking of Earth not as we know it now, not as a planet with forests, rivers, mountains, and cities, but as a very young world, still new, still forming, still finding its shape. To picture it, you might imagine a vast sphere cloaked in fire and mist, oceans not yet calm, skies not yet blue, and a silence that was broken only by the rhythms of wind, water, and volcanic breath. This is the stage upon which the first act of life would someday be written, a stage that was at once harsh and yet filled with potential. The story of life's origins is one of great patience. Billions of years have passed since the moment when the first living thing stirred, and so the questions of how, when, and why remain partly hidden in deep time. What we know for certain is that Earth itself is around 4.5 billion years old. For perhaps its first 500 million years, the surface was turbulent, covered in molten rock, with meteorites striking frequently, with no place yet for the quiet continuity we associate with life. Slowly, as the crust cooled and as water gathered into oceans, the possibility of something new began to open. Water, that most gentle and most essential of elements, filled the low places of the world, spreading across the planet to form seas that shimmered under a sun not yet as bright as the one we see today. It is in these conditions, between fire and water, between air filled with gases, very different from the air we now breathe, that the seeds of life may have first taken root. The atmosphere of the early Earth likely contained carbon dioxide, methane, nitrogen, hydrogen, and water vapor, but no oxygen. To us now, such an air would be unbreathable, yet for chemistry it was a fertile mix, ready to host reactions that, over long stretches of time, could give rise to the building blocks of biology. We might picture great clouds of steam rising from volcanic lakes, lightning crackling through thick clouds, and the steady waves of the ocean churning molecules together again and again, each encounter a chance for something new to form. As we begin to explore this topic, it is helpful to pause and think about what we mean when we say life. In our everyday sense, life means the plants and animals around us, the movement of creatures, the greening of leaves, the activity of cells. But in its most fundamental description, life means something that can grow, something that can change in response to its surroundings, something that can use energy to keep itself going, and something that can reproduce, passing along instructions from one generation to the next. These features may sound ordinary now, but in the beginning, they represented a remarkable leap. A molecule drifting freely in the ocean may persist for a while, but to begin the long road toward life, it would need the ability to copy itself, to carry forward some memory of its own shape. That is what separates the random and the fleeting from the continuous and the enduring. The origins of life, then, are not a single moment, but rather a long series of gradual steps, each one small, each one fragile, but together forming a bridge from chemistry into biology. Imagine this as a quiet unfolding. First, simple molecules form, carbon chains, amino acids, sugars. Then more complex arrangements arise, perhaps by clinging to the surfaces of minerals, perhaps by chance encounters in the restless ocean. Over time, these arrangements may have begun to interact, to link, and to assemble into systems with properties greater than the sum of their parts. From simplicity, complexity emerges, and from complexity, the potential for life. To drift further into this imagination, think of Earth at night, not with cities glowing, but with nothing more than stars above and volcanoes casting orange light into the darkness. The sea is warm, filled with dissolved minerals and gases, its surface steaming under the young Sunday. In this ocean, invisible to any eye, tiny dramas unfold. Molecules bump together, some break apart, Others hold fast. Over millions of years, what was once only random begins to take on patterns. It is here, in this subtle shift from chaos to order, that we may locate the earliest whispers of life. Though the details remain uncertain, scientists believe that this transition began more than 3.5 billion years ago. The oldest known microfossils, traces of primitive organisms, date back at least that far. Even older are chemical signatures locked in rocks, suggesting that life may have been present even earlier, perhaps close to 4 billion years ago. The thought is humbling, for it means that life took hold on Earth not long after the planet itself had settled into stability. Once conditions were right, once there was water, once the atmosphere had cooled, once energy flowed, in steady rhythms, life may have been almost inevitable. And yet, as inevitable as it might seem in hindsight, the actual path was delicate. If we think of the young Earth as a cradle, then that cradle was rocked by storms, by asteroid impacts, by sudden shifts in climate and chemistry. At any point, those first steps toward life could have faltered. And yet, somehow, they endured. The molecules persisted, the reactions continued, and out of that persistence came the ancestors of every living thing that has ever walked, swum, flown, or grown upon this planet. As you listen, let your mind wander gently to the slow passage of time. Imagine millions of years flowing past like waves upon a shore. Each wave carries away some possibilities but leaves behind others. Each wave stirs the waters where molecules meet, break apart, and rejoin. Over time, patterns emerge. The beginnings of metabolism, the use of energy, may have appeared. The beginnings of heredity, the storage of information, may have taken form. Each step small, each step patient, yet together weaving the foundation upon which all life rests. Part 1 of this lecture is not meant to provide all the details or all the theories, but rather to invite you into the calm awareness of just how vast and ancient this story island. When we speak of the origins of life, we are not speaking of a moment we could witness with our eyes. We are speaking of a time when the planet itself was different, when the very air was alien, and when the first stirrings of life were as small and fragile as dew upon a stone. To think of this is to feel both the fragility and the resilience of existence. Fragile, because it might never have happened at all. Resilient, because once it did, it has persisted for billions of years, across all changes and challenges, leading at last to the great web of life that surrounds us now. So as you rest, you may let yourself drift with the thought that life, in all its complexity, began from something so small, so quiet, that it might have been overlooked entirely. And yet, from those beginnings, the story unfolded, carrying forward through deep time. This is where our journey begins, in the stillness of an ancient ocean, in the unseen chemistry of the early Earth, and in the patient unfolding of possibility. In the next part, we will explore more closely what we mean by life, and how scientists seek to define the boundary between the living and the non-living, a boundary that was once blurred in the soft cradle of Earth's earliest days. 2. Defining what we call life. When we speak of life, it seems at first to be an easy and familiar word. We use it every day, often without pausing to think deeply about what it means. We know life when we see it in the swaying of trees, in the flight of birds, in the pulse of our own breathing. And yet, when scientists attempt to define life in precise terms, the simplicity begins to dissolve, and we find ourselves gazing at something far more intricate. For life is not just movement, not just growth, not just the sparkle of energy in a body. It is a set of characteristics, subtle and profound, that together form the boundary between the living and the non-living. To reflect on these features is to approach the origins of life with gentle clarity, because the beginnings of life on Earth must have been the beginnings of these very qualities. One of the most fundamental features of life is organization. All living things, whether as small as a single bacterium or as large as a great blue whale, are organized into structures that carry out their functions. At the smallest scale, this means the presence of cells, for the cell is the basic unit of life. A rock may be solid, a flame may flicker, but neither is made of cells. Every organism that we recognize as alive is built from cells, whether one or many. The cell is not just a container, it is a tiny, dynamic world, filled with molecules that act together in harmony. Within it, proteins fold and unfold, DNA holds instructions, and membranes carefully separate the inside from the outside. This orderliness, this architecture at the microscopic level, is the first hallmark of living systems. Yet organization alone does not suffice. Crystals, for example, form orderly structures, repeating their shapes across great spans of space, and yet they are not alive. What sets life apart is the presence of metabolism, the constant dance of energy flowing through a system. All living things take in energy from their surroundings and use it to maintain their order, to grow, and to reproduce. Plants absorb light and turn it into sugars. Animals consume food and break it down into energy. Even the smallest bacterium has pathways that convert nutrients into usable forms of energy. Without this ceaseless conversion, the order of the cell would collapse into stillness. A living being, therefore, is not static. It is a process, a continuous stream of energy transforming into form. Another feature of life is responsiveness. Living things sense their surroundings and act upon them. A plant bends toward sunlight, roots stretch downward in search of water, and bacteria swim toward nutrients while swimming away from toxins. We ourselves, without thought, adjust to light, to sound, to heat, to touch. This sensitivity shows that living beings are not closed off from the world, but are in constant dialogue with it. They take in information, they adjust, and they continue. Even the simplest organisms display this interaction, and in doing so, they reveal one of life's essential qualities. To be alive is to be aware, in however simple a form, of the world outside. Growth and reproduction are also central to what we call life. Living things change over time. They increase in size, they develop new structures, they mature, and beyond this, they create new generations, passing along their form and function. This passing down is accomplished through heredity, the transfer of instructions written in molecules such as DNA and RNA. To be alive is not only to persist in the present moment, but also to give rise to future life. In this way, life ensures continuity, linking past, present, and future in an unbroken chain. There is also the quality of adaptation. Life does not stand still, but adjusts across generations, molded by the environment. Organisms develop traits that help them survive, and those traits become woven into their descendants. Over vast spans of time, adaptation has given rise to the extraordinary diversity of life forms we see today. This slow and steady response to the challenges of existence means that life is not just a static state, but a journey, a constant shaping by the conditions of the world. Finally, there is the quiet principle of homeostasis. Living beings keep their inner world stable even when the outer world shifts. Cells maintain their balance of water and salts. Animals regulate their body temperature, and even the smallest microbe preserves the delicate chemistry within its boundaries. This balance, this careful regulation, is what allows life to continue in the face of change. Without it, the fluctuations of the environment would dissolve the fragile processes within. When we consider these features together, organization, metabolism, responsiveness, growth, reproduction, adaptation, and homeostasis, we begin to see the outline of life. Each alone is important, but together they form a pattern. To be alive is to embody this pattern, to be both ordered and dynamic, both fragile and resilient. It is a balance between structure and change, between continuity and transformation. Yet it is important to reflect that these features are not always easy to apply. Viruses, for example, blur the line. They contain genetic material and can reproduce, but only inside the cells of others. On their own, they cannot carry out metabolism, cannot maintain homeostasis. Are they alive? Some say yes, others say no. They are perhaps best understood as entities at the edge of life, reminders that the definition we create is not absolute, but a useful guide. The origins of life must have passed through similar gray zones, stages in which molecules displayed some qualities of life but not all, stages where organization was present, but reproduction was not yet stable, or where replication occurred, but without metabolism. By defining life in this way, we also prepare ourselves to think about how it began. Each of these features must have had a beginning, a first appearance on the stage of Earth, the first metabolism, the first replication, the first boundary between inside and outside. All these must have emerged step by step. To reflect on the definition of life is to reflect on its assembly, the way simple processes combine to become something altogether new. As you lie quietly and listen, you might imagine this definition as a gentle framework, like a soft outline of a shape. Into this outline, chemistry slowly painted details until, at last, the picture became recognizable. Organization, responsiveness, reproduction, all these came together like notes in a melody, each alone, not yet music, but together, forming the song of life. In this calm reflection, we see that life is not just a matter of being or not being, but of unfolding. From chemistry, qualities appeared. From qualities, systems arose. From systems, continuity and diversity flowed. To define life is therefore not only to describe what exists now, but to trace back the faint beginnings of a process that has been ongoing for nearly 4 billion years. In the next part of our journey, we will turn our attention outward once more, to Earth itself. In its earliest days, we will picture the young planet as it cooled and settled, and we will imagine the oceans and skies in which these first qualities of life may have begun to stir. 3. Earth's birth and early conditions. To continue our gentle exploration, we now step back in time to picture the Earth not as the home we know, but as it was in its earliest youth. The Earth we see today, with its blue oceans, green forests, and delicate balance of life, is the result of billions of years of slow and steady change. But if we imagine Earth as it was just after its formation, more than 4.5 billion years ago, we encounter a world almost unrecognizable. It was a place of fire and stone, a planet still forming, still finding its rhythm, still too harsh to host the delicate chemistry of life. Yet even in those conditions, the foundations for what would become life were already being laid, quietly, patiently, beneath the restless skies. The birth of Earth itself was the outcome of cosmic processes that began long before. The solar system formed from a cloud of gas and dust, remnants of earlier stars that had lived and died. Within this cloud, gravity pulled particles together, slowly building larger and larger bodies. The young sun ignited at the center, and around it, planets began to form. Earth was one of these, emerging from collisions of smaller rocky bodies. These impacts were frequent and violent, and each one released great amounts of heat. For a long time, the surface of Earth was molten, a glowing sphere of magma, unstable and inhospitable. In time, as the planet grew larger, gravity held it more firmly together. Heavier materials, like iron and nickel, sank inward, forming the core, while lighter rocks floated upward, becoming the crust. This separation created the layers of the planet, with the solid inner structures and the dynamic outer regions that we still live upon today. Yet the crust in those earliest days was fragile and often broken by impacts from asteroids and comets. These collisions shaped the surface, brought in new materials, and may even have delivered water and organic molecules from space, seeding the young world with ingredients it would later need. The atmosphere of early Earth was not like the air we now breathe. It was thick with carbon dioxide, methane, nitrogen, and water vapor. Oxygen, which now fills every breath we take, was almost entirely absent. To us, such air would have been suffocating, but for the processes of chemistry, it provided a fertile field. Lightning flickered through these heavy clouds, and volcanic eruptions filled the sky with gases. The sun was dimmer than it is today, casting a paler light. Yet the surface was warmed by the greenhouse effect of the atmosphere. Oceans began to collect as water vapor condensed, filling low-lying regions with vast seas. It was within these waters that the earliest steps toward life would later unfold. We might imagine standing at the edge of one of those primordial oceans. The sky above is a hazy red or orange, colored by volcanic gases. The land is barren, made of dark rocks and cooling lava. Steam rises where water meets hot stone, and the air is thick with the scent of sulfur and minerals. It is a harsh world, but not a silent one. Waves crash, geysers hiss, and the deep rumble of eruptions rolls across the horizon. This is Earth in its infancy, restless and raw, yet already carrying within it the potential for life. The oceans themselves were different from the seas we know. Rich with dissolved minerals, they may have been greenish or brown, opaque rather than clear. Into these waters flowed chemicals from the atmosphere and from the rocks. Carbon compounds mingled with nitrogen, sulfur, and metals, stirred by tides and currents. Lightning and ultraviolet radiation from the young sun added energy, driving reactions that built new molecules. Over time, these molecules accumulated, forming what scientists sometimes call the primordial soup, a mixture that contained the raw ingredients of life. Even as conditions were harsh, the earth was cooling and settling into rhythms. Volcanoes still erupted, but the crust was hardening. The cycles of day and night began to regulate temperatures. The pull of the moon, formed after a great impact early in Earth's history, created tides, stirring the oceans and moving their contents back and forth. These steady patterns created opportunities for chemistry to repeat itself, over and over, until chance arrangements became persistent patterns. It is thought that the earliest evidence of life appears not long after this period of stabilization. Rocks more than 3.5 billion years old contain traces of carbon that may be the remains of ancient organisms. Stromatolites, layered structures built by microbial communities, appear in the fossil record from this time. These hints suggest that life began surprisingly early, within only a few 100 million years after the Earth cooled enough to support liquid water. That speed is striking, and it suggests that once the right conditions were present, the steps toward life may not have been rare, but almost a natural unfolding. And yet, if we think carefully, the conditions that made life possible were delicate. Too much heat, and molecules would break apart before they could form complex structures. Too little energy, and reactions would stall. Too violent an impact from space, and oceans could be vaporized, setting back progress by millions of years. The fact that life began at all speaks to a balance, a narrow window of opportunity that Earth managed to maintain. It was neither too hot nor too cold, neither too dry nor too unstable. It was, in its own way, just right. As you rest and listen, imagine the immensity of time passing. Imagine the planet cooling, its surface shifting from fire to stone, its skies from fire-filled to water-filled. Picture the first rains falling on still hot rock, hissing as they touched the ground, running into streams that carved the first channels. Imagine those streams flowing into seas that spread wider with each passing age. In those waters, unseen to any eye, chemistry stirred quietly. From this chemistry would one day emerge life. But for now it was only a patient waiting, a slow weaving of possibilities. To think of Earth in these earliest days is to see how life's beginnings were tied to the planet itself. Without water, without a stable crust, without the gases of the atmosphere, there would have been no stage for life to arise. Earth was not yet alive, but it was already preparing, already offering a home for what was to come. The minerals of the rocks, the heat of the vents, the energy of the storms, the motion of the tides, all of these work together to create the conditions in which life could emerge. So, in this part of our journey, we rest with the image of the young Earth, vast, preparing to host the miracle of life. In the next part, we will turn more closely to the oceans themselves, those great cradles of chemistry, and to the way water shaped and supported the very first steps toward living systems. 4. Water. Water as the cradle of life. When we imagine the Earth as it was in its earliest stable state, one image rises above all others. The ocean stretching wide across the surface, filling low-lying basins with water that would become the great stage upon which life began. It is difficult to overstate the importance of water, for it is more than a backdrop, more than a passive setting. Water is the very medium that made the chemistry of life possible. In its gentle fluidity, it carried molecules from place to place, dissolved minerals from the rocks, and provided a space where reactions could occur again and again, unhindered by the stillness of dry land. Without water, the story of life could never have been written, and so to understand the origins of life is to spend time with water itself, to see how it cradled and nurtured the first fragile steps of biology. Water is a remarkable substance, both simple and profound. Each molecule is made of 2 atoms of hydrogen, bonded to 1 atom of oxygen, a small arrangement that hides surprising powers. Water is polar, meaning it carries tiny charges that allow it to interact with many other molecules. This polarity makes it an excellent solvent, able to dissolve salts, gases, and organic compounds. For early Earth, this meant that the oceans became vast laboratories, collecting ingredients and holding them in suspension. Where other solvents might have been too limited or unstable, water provided both stability and flexibility. It cushioned reactions, prevented delicate structures from breaking apart too quickly, and allowed fragile molecules to persist long enough to interact with one another. Imagine the earliest rains falling on Earth's hot surface. Each drop carried with it gases from the atmosphere, washing them into streams and lakes. Those streams in turn picked up minerals from the rocks, carrying ions of iron, magnesium, sodium, and many others into the seas. Lightning split through the heavy skies, driving chemical reactions in the air, and the products of those reactions dissolved in the water below. Ultraviolet light from the young sun struck the ocean surface, breaking bonds and creating new arrangements, which the waves mixed into the depths. In this way, the oceans became rich in potential, a mixture of countless ingredients stirred by winds, tides, and currents. It is within this liquid cradle that many scientists believe the first building blocks of life formed. Amino acids, the components of proteins, are known to arise from simple gases and energy, and once formed, they are easily dissolved in water. Nucleotides, the building blocks of RNA and DNA, can also accumulate under such conditions, though they are more fragile and complex. Lipids, molecules with both water-loving and water-fearing parts, may have assembled into simple spheres, enclosing pockets of water within. These spheres, known as protocells, could drift and merge, creating tiny chambers where chemistry was sheltered from the open sea. Each of these developments depended on water's ability to host reactions and to support delicate structures without destroying them. Water also provided cycles, the constant rhythms that encouraged repetition and refinement. Waves broke molecules apart and then brought them together again. Tides carried substances from shallow pools to deeper waters and back. In coastal regions, drying and wetting cycles may have concentrated certain molecules, allowing them to link into longer chains before being released once more into solution. These cycles of dilution and concentration, of stillness and stirring, acted like nature's experiments, testing countless combinations until some began to persist. Over immense spans of time, chance arrangements that could copy themselves or interact productively with their neighbors would slowly become more common. We can think of water not only as a cradle but also as a shield. The early Earth was a dangerous place, with radiation from the sun and impacts from space, threatening fragile molecules. Deep within the oceans, however, protection was offered. Ultraviolet rays were absorbed before they could reach far below the surface, and the water itself buffered against sudden changes in temperature or chemistry. Hydrothermal vents, in particular, may have provided sheltered environments where mineral-rich fluids met cooler seawater, creating gradients of heat and chemistry that powered reactions. In such places, the constant flow of water carried nutrients and energy, while mineral surfaces provided scaffolding for molecules to attach and grow more complex. Even today, all known life depends on water. Every cell carries water within it, surrounding proteins and nucleic acids, enabling enzymes to fold and unfold, and transporting nutrients and wastes. The chemistry of life as we know it cannot proceed without it. This universality suggests that water has always been essential, that its role is not incidental but fundamental. In considering the origins of life, this truth becomes even more striking. Wherever life first began, it almost certainly began in water, whether in shallow pools warmed by sunlight, in lakes rich with dissolved gases, or in the depths of the ocean near hydrothermal vents. It is soothing to reflect that water itself may be far older than Earth. Some of it may have formed in the cold depths of space, frozen in comets and icy grains, later delivered to the planet by impacts. Some may have been released from deep within Earth's mantle through volcanic activity. In either case, water was present from the earliest times, shaping not only the surface of the Earth but also the very possibility of life. It is a reminder that life is deeply tied to cosmic processes, that the molecules we now depend upon may have drifted through the universe long before Earth was born. As we continue our quiet journey, imagine again the vast oceans of early Earth. They are not yet blue as we see them today, but perhaps green or brown, rich with dissolved minerals. Their surfaces steam beneath the sun, and their depths are stirred by tides and currents. Within them, molecules drift and meet, forming fleeting bonds, breaking apart, and meeting again. Over millions of years, these interactions become patterns, and from patterns come the beginnings of order. The oceans are not merely water. They are the workshop of life, the cradle in which the first delicate rhythms of biology began to stir. Water's role as cradle is also symbolic. Just as a cradle holds and protects the most fragile beginnings of life, so too did the oceans of Earth hold and protect the chemistry that would become living systems. The cradle rocks gently, stirred by tides, warmed by sunlight, cooled by night, and through this rocking, molecules were given the chance to become more than they were. From the stillness of minerals and gases, motion arose. From the motion, patterns, and from the patterns, life itself. As you rest and listen, you may think of the water that surrounds us even now, the rivers and lakes, the seas and oceans, the rain that falls and the snow that melts. Each drop is part of a lineage that stretches back to those earliest days, when water first filled the earth and offered itself as a cradle for life, to drink, to bathe, To feel rain upon your skin is, in a sense, to touch the same water that once sheltered the origins of all living things. And so, in this part of the lecture, we pause with the thought that water was not only necessary but nurturing, not only a solvent but a sanctuary. It was the gentle medium that gave chemistry time to grow into biology, that allowed fragility to endure until it became resilience. In the next part, we will move closer to one of the most enduring ideas in this story, the notion of the primordial soup, a vision of oceans enriched with organic molecules, simmering with the potential of life. 5. The primordial soup. To understand the earliest origins of life, many scientists and thinkers have turned to an evocative image, often described as the primordial soup. It is a phrase that conjures a sense of warmth and nourishment, a great broth simmering beneath the skies of the young earth, filled with ingredients that, over time, could assemble themselves into living matter. The idea suggests that in the oceans of our planet, billions of years ago, molecules gathered together in such abundance, and with such variety, that the conditions became ripe for something entirely new to arise. The concept is not a single explanation, but rather a vision, one that captures the imagination and provides a framework for thinking about how lifeless chemistry could slowly and gently cross the threshold into biology. The primordial soup hypothesis suggests that the oceans of early Earth were rich in organic molecules, compounds made of carbon and hydrogen, sometimes with oxygen, nitrogen, sulfur, or phosphorus as well. These are the building blocks of life, the raw materials that form amino acids, nucleotides, lipids. Unlike the clean blue waters we see today, these oceans may have been cloudy, murky, and dark, infused with chemicals from volcanic eruptions, lightning storms, and hydrothermal vents. Each new contribution added ingredients to the mix. The concentration of these molecules, it was, in essence, a global experiment in chemistry, carried out slowly and patiently under the changing skies of the young planet. One of the most compelling features of the primordial soup idea is its simplicity. When we look at the complex forms of life today, from towering trees to delicate insects, it is difficult to imagine such complexity appearing all at once. The soup model offers a softer vision. Life began not as a sudden leap, but as a gradual accumulation. Molecules formed, combined, and interacted, until eventually they began to show patterns that resembled living behavior. This perspective eases the mind into the enormity of the concept, allowing us to picture life's origin as a gentle unfolding, rather than an abrupt spark. We can imagine these ancient seas as warm and shallow in some places, deep and dark in others, each environment contributing in its own way. In tidal pools along rocky shores, water evaporated under the sun, leaving behind concentrated solutions where molecules bumped into each other more frequently. In the depths of the ocean, vents released streams of minerals and heat, creating gradients that powered reactions. Everywhere, the constant motion of water stirred and mixed, ensuring that molecules did not remain isolated but were always meeting, parting, and meeting again. Each of these encounters was a chance, however small, for something new to form. The primordial soup hypothesis first gained scientific expression in the early 20th century, when researchers such as Alexander Oparin and J.B.S. Haldane proposed that the early Earth's atmosphere and oceans could have supported the spontaneous formation of organic compounds. They imagined a world without oxygen, where energy from lightning and ultraviolet radiation encouraged simple molecules to join into more complex ones. They suggested that over time, these molecules accumulated in the oceans, gradually becoming more diverse and more capable of complex behavior. Their ideas were speculative at first, but they laid the foundation for decades of experiments and explorations that followed. The most famous of these experiments was carried out in 1953 by Stanley Miller and Harold Urey. They built an apparatus that simulated the conditions thought to exist on the early Earth, a mixture of gases such as methane, ammonia, hydrogen, and water vapor, along with electrical sparks to represent lightning. After running the experiment for days, they discovered that amino acids had formed in the liquid water. Amino acids are the fundamental components of proteins, and proteins are central to all life. This result offered powerful support to the idea that life's building blocks could arise naturally in a primordial soup. While the precise details of Earth's early atmosphere remain debated, the experiment captured the imagination of the scientific world and gave weight to the vision of oceans rich in organic potential. It is worth pausing here to think about the patience of this process. The oceans were vast, and the molecules within them were tiny. A single reaction, a single bond forming between two atoms, is almost insignificant when seen in isolation. But over millions upon millions of years, with countless waves, countless storms, and countless cycles of concentration and dilution, even the rarest events could accumulate. The soup did not need to produce life instantly. It only needed to allow the slow gathering of molecules into more stable and complex arrangements. Over time, these arrangements could begin to copy themselves, to interact with one another, and to persist against the randomness of their surroundings. As we drift in thought, we might picture the primordial soup as a vast canvas, painted with colors we cannot now see. Perhaps it shimmered green with dissolved minerals. Perhaps it glowed faintly under the dim sunlight filtered through a haze of volcanic gases. Within this canvas, molecules drifted like brushstrokes, forming shapes that were erased and redrawn again and again. In this ceaseless movement, patterns began to emerge, like the first outlines of a figure slowly appearing from abstract lines. These patterns were fragile, easily lost, but some endured, and in their endurance lay the first whispers of life. It is important to recognize that the primordial soup is not a complete explanation of life's origins. It is a metaphor, a way of seeing. Some scientists argue that life may have begun not in the open oceans but in more sheltered places, such as deep-sea vents or within mineral pores. Others suggest that molecules could not have survived long enough in a global ocean to organize into life. Yet even as debates continue, the image of the soup remains powerful because it captures something essential, that life arose from the natural chemistry of the earth, nurtured by its waters and energized by its storms. Even today, traces of this origin linger. The chemistry of our own bodies reflects the chemistry of the seas. Our blood contains salts in proportions that echo the composition of ancient oceans. The water within our cells is a reminder that life began in liquid, not on dry land. When we speak of the primordial soup, we are not only imagining the distant past but also acknowledging that we carry part of that story within us. Each breath, each heartbeat, each thought is supported by molecules that once drifted in ancient waters, long before there were creatures to name them. And so the primordial soup remains a gentle yet profound idea, a world where oceans served as both kitchen and cradle, simmering with ingredients, stirred by time, and slowly transforming chemistry into biology. It is not the whole story, but it is a beginning, a way of picturing how life might arise, not from miracle, but from the steady patience of nature. In the next part, we will turn to the experiments that sought to recreate these early conditions in laboratories, focusing in particular on the Miller-Urey experiment, which gave humanity its first real glimpse of how the soup might have worked. 6. Energy sparks in a young world. When we think of the early Earth, it is easy to picture only still oceans and barren rocks. But the reality was far more dramatic, filled with energy in many forms, each one shaping the environment and stirring the chemistry that would eventually lead to life. The young planet was restless. Volcanoes rumbled and spewed molten rock. Lightning danced across thick clouds. The sun bathed the surface in ultraviolet light, and beneath the seas, Vents released heat and minerals into the water. This was not a quiet world, but a place alive with forces that continuously reshaped its surface and its atmosphere. These sources of energy were not simply destructive, they were also creative, driving the reactions that turned simple gases into complex organic molecules. Energy, in all its forms, was the spark that turned Earth from a barren sphere into a cradle for life. Consider lightning first, a force that has always fascinated human beings. On the early Earth, lightning would have been far more frequent than today, because the atmosphere was unstable and storms raged often. Each bolt carried immense energy, enough to split molecules apart and force new ones to form. When lightning passed through clouds rich in methane, ammonia, and water vapor, it could drive the creation of amino acids and other organic compounds. This process, repeated countless times across millions of years, would have enriched the oceans with the building blocks of life. It is humbling to imagine that what we see as a momentary flash in the sky might have been one of the great engines of life's beginnings, shaping molecules in ways that otherwise might never have occurred. The sun, too, played its role, though not in the gentle way we experience it today. 4 billion years ago, the sun was fainter in overall brightness, but it released intense bursts of ultraviolet radiation. Without a protective ozone layer, much of this radiation reached the surface of Earth. To living organisms now, such radiation is harmful, damaging DNA and proteins. But before life existed, ultraviolet light may have been a catalyst, breaking chemical bonds and allowing new ones to form. When it struck gases in the atmosphere or compounds dissolved in shallow waters, it provided a steady stream of energy that fueled chemical reactions. Some of the earliest nucleotides, the molecules that form RNA and DNA, may have been created in part by the work of ultraviolet light. What is harmful to life now may once have been essential for life to begin. Volcanic activity offered another powerful source of energy. In the young Earth, volcanoes were far more active than they are today, releasing heat, gases, and minerals in great abundance. Each eruption filled the skies with steam, carbon dioxide, methane, and sulfur compounds, all of which entered the oceans through rain and runoff. Lava flows created new land, only to be broken apart again by further eruptions. This cycle enriched the environment with raw materials, constantly replenishing the chemistry of the oceans. At the same time, the heat from volcanic regions drove chemical gradients, differences in temperature and pressure that can power reactions. Around hot springs and vents, water and gases mixed, creating conditions that may have encouraged the assembly of organic molecules. These fiery processes, though dangerous in appearance, provided energy and ingredients for life's earliest steps. Beneath the oceans, hydrothermal vents released mineral-rich fluids into the water. These vents were driven by the heat of Earth's interior, where seawater seeped into cracks, heated, and emerged laden with metals and chemicals. Around these vents, striking environments formed, towering chimneys of minerals, clouds of hot fluid mixing with cold seawater, and gradients of heat and chemistry that persisted for long periods of time. Modern life thrives in such places, with unique communities of organisms, supported not by sunlight but by chemical energy. It is possible that life itself began in these environments, where energy flowed steadily, and where minerals provided surfaces upon which molecules could assemble. The vents offered both energy and shelter, protecting fragile chemistry from the harsher conditions at the surface. It is important to recognize that energy alone is not enough. Energy must be harnessed in ways that encourage order rather than chaos. Too much energy can destroy molecules, breaking them apart as quickly as they form. Too little, and nothing new can arise. What made Earth special was not just the presence of energy, but the balance of different sources, some gentle, some intense, all contributing in different ways. Lightning created sudden bursts of complex molecules. Ultraviolet light provided a steady flow of energy for new reactions. Volcanoes and vents added heat and minerals in constant supply. Together, these forces created a world that was dynamic, but not impossible. A world where the chemistry of life could persist and evolve. When we imagine this young planet, it is easy to think of energy as violent and overwhelming. Yet in the grand span of time, these forces were part of a patient process. Each spark of lightning, each ray of sunlight, each plume of volcanic gas was a single step in a journey that lasted millions of years. The oceans received the products of these events again and again, slowly becoming enriched with molecules that could interact in increasingly complex ways. Energy was the artist, and the earth was its canvas, painted over and over until patterns emerged that would one day be recognized as the beginnings of life. As you rest and listen, you might picture a stormy sky above a young ocean. Lightning flashes, thunder rolls, and rain falls onto volcanic rocks. The water runs into the sea, carrying minerals with it. Beneath the surface, hot vents release streams of chemicals into the depths. Sunlight filters through the haze of the atmosphere, its ultraviolet rays striking the surface. In this restless world, molecules drift and combine, shaped by the endless play of energy. It is not a single moment, but a continuous unfolding, a rhythm that repeats for millions of years until fragile order begins to emerge. Even today, life depends on energy in all its forms. Plants capture sunlight to build sugars. Animals consume food and release energy from it. Deep-sea microbes use chemical gradients to power their metabolism. In every case, life is a process of capturing and directing energy, just as the earliest molecules did when they first began to interact in the oceans of the young Earth. The story of life's beginnings is, in many ways, the story of how energy was harnessed, step by step, from random sparks into organized processes that could sustain and reproduce themselves. In reflecting on energy's role, we see that the conditions of early Earth were neither too calm nor too chaotic. They were balanced in a way that allowed molecules to persist, yet encouraged them to change. The planet itself was the laboratory, and its storms, eruptions, and sunlight were the tools. Out of this interplay, the foundations of life were laid. And so, as this part draws to a close, we may rest with the thought that energy was both the challenge and the gift of the young Earth. It destroyed and created, broke apart and built anew, until at last, through countless cycles, it shaped the molecules that would one day awaken as life. In the next part, we will look more closely at one of the most famous attempts to recreate these ancient conditions, the Miller-Urey experiment, a landmark in science that offered a glimpse of how sparks in a young world could give rise to the chemistry of life. 7. The Miller-Urey experiment. In the long story of humanity's attempts to understand its own beginnings, there are certain moments that stand as quiet landmarks, points where curiosity and patience brought a little more light to a great mystery. One of the most memorable of these came in the mid-20th century, when two scientists, Stanley Miller and Harold Urey, set out to recreate, in the controlled setting of a laboratory, the possible conditions of the young Earth. Their work is remembered now as the Miller-Urey experiment, and though it was modest in scale, it offered one of the first glimpses of how lifeless molecules could be coaxed into forming the building blocks of life. In many ways, it gave shape to the idea of the primordial soup, showing that such a vision was not just poetic speculation, but something that could be tested and observed. To imagine their experiment, let us first recall the picture of early Earth. The planet was covered by oceans, its skies heavy with gases such as methane, ammonia, hydrogen, and water vapor. There was no oxygen in the atmosphere, and the world was stirred by constant energy, lightning, ultraviolet radiation, volcanic eruptions. Within this setting, Oparin and Haldane, two scientists of the earlier 20th century, had suggested that organic molecules might form spontaneously, gathering in the oceans until they reached levels capable of supporting life's first steps. Miller and Urey sought to test this idea directly. Could simple compounds, given the right atmosphere and energy, really produce amino acids, the very ingredients of proteins? The experiment itself was elegant in its simplicity. Miller and Urey constructed a closed apparatus of glass tubes and flasks, designed to mimic the early Earth's environment. At one end, a flask of boiling water represented the young oceans, sending water vapor into a chamber containing methane, hydrogen, and ammonia. This mixture of gases stood in for the primitive atmosphere. Electrodes were placed in the chamber to deliver sparks, simulating the lightning that would have flashed frequently across ancient skies. The gases and water vapor cycled continuously through the system, condensing, mixing, and evaporating again, just as they would have done in nature. For days the experiment ran, the sparks crackling through the mixture, the water boiling and condensing, the gases swirling and recombining. The liquid that collected in the lower part of the apparatus began to change, taking on a reddish-brown color. When Miller analyzed it, he found that amino acids had formed. These are the fundamental units of proteins, the molecules that carry out nearly every function of life. Not only had amino acids appeared, but several different kinds were present, including some that are used universally by living organisms today. It was a stunning result. With nothing more than simple gases, water, and sparks of energy, molecules central to life had emerged. The importance of this finding was not in its complexity, but in its implication. If such molecules could form so readily in a small glass chamber over the course of a few days, how much more could have formed in the vast oceans of Earth over millions of years? The experiment showed that organic molecules need not have been delivered from space, nor created by some extraordinary event. They could arise naturally, under conditions that were likely present on the young Earth. The boundary between non-living chemistry and the first steps toward life suddenly seemed a little narrower, a little less mysterious. It is worth remembering, though, that the Miller-Urey experiment did not create life. It did not even create proteins, nucleic acids, or cells. What it did show was that the path from simple gases to the building blocks of biology was plausible. The leap from amino acids to living organisms is still vast, but the first step had been demonstrated in a way that could not be dismissed. The experiment gave confidence to the idea that life might emerge from natural processes, guided not by miracle but by the steady hand of chemistry and energy. In the decades since, variations on the Miller-Urey experiment have been carried out many times. Scientists have tested different mixtures of gases, different sources of energy, and different settings meant to simulate hydrothermal vents or shallow pools. Each time, organic molecules have been produced: amino acids, nucleotides, sugars, and lipids. The details vary, but the message is consistent. The chemistry of life's ingredients is not difficult to achieve under the right conditions. It seems almost inevitable, given enough time and space. This strengthens the idea that the primordial soup, whether in oceans, lakes, or vent systems, was indeed rich with the potential of life. There have been criticisms and refinements, of course. Some scientists point out that the early Earth's atmosphere may not have been as rich in methane and ammonia as Miller and Urey assumed. Others suggest that ultraviolet radiation, rather than lightning, was the more important source of energy. Still others emphasize the role of minerals and surfaces in stabilizing and concentrating molecules. These debates do not diminish the significance of the experiment. Rather, they highlight how science evolves, with each new insight building upon earlier ones. The Miller-Urey experiment remains a foundation, a proof of principle, even if the exact details of early Earth differ from the apparatus they built. Beyond its scientific importance, the experiment has a poetic quality. To picture sparks of electricity dancing through a chamber of gases, giving rise to the same molecules that make up our bodies, is to feel a connection between the present and the distant past. It is to recognize that life's roots are not shrouded in unreachable mystery, but can be traced, at least in part, to natural processes that we can reproduce, however humbly, in our laboratories. The thought carries a quiet reassurance. Life is not an accident, but a possibility, one that arises when the right ingredients and the right energies are brought together. As we reflect on this, imagine again the early Earth, storms flashing across a restless sky, rain falling into oceans heavy with minerals, gases swirling and mixing, energy sparking through the air. Imagine, too, the small molecules forming in those waters, fragile, yet persistent, accumulating over time. The Miller-Urey experiment gives us a way to see this vision not as speculation, but as a glimpse of what might truly have happened. It transforms the primordial soup from metaphor into mechanism, from idea into something tested and tangible. Even today, the results resonate. In classrooms and textbooks, the experiment is often one of the first introductions to the scientific study of life's origins. For many, it is a reminder that even the greatest mysteries can be approached with simple questions and careful tests. The apparatus itself, now preserved in museums, stands as a quiet symbol of human curiosity, a reminder of how much can be learned by daring to ask how life began. And so, as this part of the journey comes to rest, we are left with the image of sparks dancing through a chamber and of molecules quietly forming in their wake. From these molecules, more complex chemistry would follow, and from that chemistry, the first hints of self-replication and organization. In the next part, we will leave the surface storms behind and journey to the depths of the ocean, where hydrothermal vents offered another kind of cradle, a place of heat, minerals, and gradients where life may have found another path to its beginning. 8. Beyond the soup, hydrothermal vents. When we picture the origins of life, it is natural to imagine the surface of the earth, the wide oceans under stormy skies, lightning flashing above, and molecules forming in shallow pools. Yet another possibility lies not at the surface but in the hidden depths, far below the waves, where sunlight does not reach, and the world is illuminated instead by the glow of heat from within the earth itself. This is the realm of hydrothermal vents, places where seawater seeps deep into the crust, becomes heated by molten rock, and then rises back upward, carrying with it a rich mixture of minerals. Around these vents, strange landscapes appear, chimneys of stone that release dark plumes of superheated water, filled with sulfur and metals. It is in such environments, some scientists believe, that life may have first taken hold, sheltered by the sea and nourished by the steady flow of energy and chemistry. Hydrothermal vents are among the most remarkable features of our planet. They were first discovered in the late 20th century, surprising oceanographers who expected the deep ocean floor to be barren and lifeless. Instead, they found towering vent structures, sometimes called black smokers, rising like chimneys from the seafloor, billowing with hot fluid. Around these vents, they saw communities of life, giant tube worms, clams, crabs, and countless microbes, thriving in total darkness, without any need for sunlight. These ecosystems were powered not by photosynthesis but by chemosynthesis, the process of using chemical energy from the vent fluids to build organic matter. It was a revelation, proof that life could exist in places where the sun had no influence. This discovery reshaped the way scientists thought about life's boundaries, and, by extension, its beginnings. If life can flourish now around hydrothermal vents, could it also have begun there billions of years ago? The idea is compelling. Vents provide a continuous source of energy, not in sudden flashes like lightning, but in steady gradients of heat and chemistry. They also supply minerals that can act as catalysts, surfaces upon which molecules can gather and react. The porous structures of vent chimneys create tiny chambers, almost like natural laboratories, where reactions can occur in concentrated spaces. Within these microenvironments, simple molecules may have been coaxed into forming more complex structures, shielded from the turbulence of the wider ocean. One of the strongest arguments in favor of hydrothermal origins is the presence of gradients. Life as we know it depends on gradients, differences in concentration, in temperature, in electrical charge. Cells today use such gradients across their membranes to power metabolism, moving ions from one side to another to drive chemical reactions. Hydrothermal vents naturally create such gradients, with hot, mineral-rich fluids meeting cold seawater. In this interface, energy flows constantly, a natural power source for the chemistry of life. It is easy to imagine how primitive systems might have exploited these gradients long before the first true cells evolved. Minerals within the vents may also have played an essential role. Iron and sulfur compounds, abundant in vent fluids, are excellent catalysts. They can encourage chemical reactions that would otherwise occur only slowly or not at all. Some researchers suggest that the first metabolic pathways, the series of reactions that cells use to harvest and store energy, may have begun on the surfaces of such minerals. In this vision, metabolism came before heredity, with simple cycles of reactions sustained by the vent environment. Over time, these cycles may have become linked to molecules like RNA, creating systems that could both process energy and store information. It is soothing to consider how natural and patient this process might have been. Imagine tiny bubbles within vent structures, filled with mineral-lined walls, warmed by heat from below, cooled by seawater from above. Within these bubbles, molecules drift and meet, sometimes forming stable arrangements. Some arrangements break apart, others persist, and over long stretches of time, those that persist become more common. Eventually, the chemistry takes on qualities that we would call life: self-maintenance, energy use, even self-replication. From the quiet flow of water and minerals, something entirely new emerges. The hydrothermal vent hypothesis also offers an explanation for why the earliest known organisms on Earth are often extremophiles, microbes that thrive in conditions of heat, pressure, or chemical harshness. The ancestors of life may have been adapted from the start to such environments, and their descendants carried these traits forward. Today, we find microbes living not only around vents, but in boiling hot springs, in acidic lakes, and even deep within rocks. These extremophiles remind us that life is not fragile but remarkably resilient, and that its beginnings may have been shaped in places we once thought uninhabitable. There is also a cosmic dimension to this idea. If life can begin in hydrothermal vents on Earth, perhaps it can do so elsewhere. Icy moons such as Europa and Enceladus are believed to harbor oceans beneath their frozen surfaces, warmed by tidal forces and dotted with hydrothermal activity. Plumes of water vapor have even been observed spraying from Enceladus, hinting at subsurface vents. If life can emerge in such places, then the story of biology may not be unique to Earth. It may be written wherever there are oceans, rocks, and the steady flow of heat and minerals. Despite its appeal, the hydrothermal vent hypothesis is not without challenges. Some argue that the high temperatures near vents would destroy fragile molecules as quickly as they form. Others suggest that vents are too isolated, that molecules formed there would remain trapped rather than spreading across the oceans. Still, the idea continues to inspire research, and laboratory experiments have shown that under the right conditions, vents can indeed encourage the formation of complex organic molecules. Whether they were the birthplace of life or simply one of many nurturing environments, they remain a vital piece of the puzzle. To picture this possibility is to imagine a world hidden from the sun, where the deep sea is utterly dark, yet alive with unseen chemistry. The water is cold, but near the vents, it glows with heat. Mineral towers rise like chimneys, their surfaces rough and porous. Within their hollows, bubbles of fluid churn and settle. In these chambers, chemistry stirs, quietly and persistently, until, across spans of time, we cannot truly comprehend, the chemistry begins to resemble biology. No eye sees it, no creature notices it, but something irreversible has begun. And so, the story of life may have been written not only in the open oceans, under stormy skies, but also in the hidden depths, where Earth's own heat provided the spark. Whether or not hydrothermal vents were the sole birthplace of life, they remain a powerful reminder that beginnings can come in many forms, and that life may arise wherever conditions allow chemistry to persist and evolve. In the next part of our journey, we will turn to another idea, one that looks not to heat or minerals, but to molecules themselves, the RNA world hypothesis, which suggests that before DNA and proteins, RNA may have been the key to life's first steps. 9. The role of minerals and surfaces. When we imagine the origins of life, it is tempting to picture everything happening in the open waters of the ancient seas, with molecules drifting freely until chance encounters gave rise to something new. Yet for all their richness, the oceans posed a challenge. Molecules dissolved in water tend to remain dispersed, and fragile chains can be broken apart before they have time to grow more complex. To move from chemistry to biology, there needed to be not only the right ingredients and the right energy, but also some way of bringing those ingredients together, holding them close long enough for patterns to emerge. This is where the earth itself may have lent a gentle hand, through the surfaces of minerals and rocks that offered structure, shelter, and stability to fragile molecules. In this vision, the solid earth was not merely a stage for life, but an active participant, guiding the first steps through the quiet properties of its surfaces. Minerals are more than inert substances. Their surfaces can attract and bind molecules, holding them in place in ways that increase the likelihood of reactions. On the early Earth, clays, iron sulfides, and other mineral compounds were abundant, produced by volcanic activity, weathering, and hydrothermal vents. Each grain of mineral provided a tiny landscape, with grooves, pores, and charge sites that could capture organic molecules from the surrounding water. Instead of drifting endlessly in the vast ocean, molecules attached themselves to these surfaces, where they could be concentrated and brought into proximity with others. This concentration was essential, for chemical reactions require molecules to meet often enough to form bonds. On the vast scale of the oceans, such meetings might be rare, but on the scale of a mineral surface, they became more frequent and more likely to persist. Clays are often singled out in this context because of their layered structure and their natural tendency to absorb organic compounds. The sheets of clay minerals can act almost like pages of a book, trapping molecules between them. Within these spaces, reactions can occur with greater efficiency, shielded from the turbulence of the open sea. Some experiments have shown that clays can even encourage the linking of nucleotides into chains, a step toward the formation of RNA or DNA. In this way, clay may have been more than a passive surface. It may have been a teacher, guiding molecules into patterns that would later become central to biology. Iron and sulfur minerals, abundant around hydrothermal vents, also offer intriguing possibilities. Their surfaces are known to catalyze reactions that are part of modern metabolism, such as those involving carbon dioxide and hydrogen. Some researchers suggest that the earliest metabolic cycles, the kind of chemical pathways that later became essential to cells, may have originated on these mineral surfaces. The rocks themselves provided both structure and chemistry, creating small chambers where energy and matter could interact in sustained ways. It is soothing to imagine these chambers as tiny laboratories scattered across the seafloor, each one quietly conducting experiments for millions of years, until one of them produced something truly new. The role of minerals is not only in concentration and catalysis, but also in stability. Molecules floating in the ocean are subject to disruption by heat, radiation, or simple dilution. Bound to a surface, they gain protection. Pores and grooves can shelter fragile chains from harsh conditions, allowing them to survive longer. This increased longevity gave molecules time to explore more complex arrangements, to fold and refold, to link and unlink, until stability was found. Without such shelter, the earliest polymers might never have persisted long enough to become meaningful. There is a quiet poetry in the thought that the very rocks of the earth shaped the origins of life. Minerals are ancient, born of the planet's cooling and shifting, yet they may have served as midwives for something entirely different from themselves. They offered their surfaces freely, holding onto molecules, guiding them toward complexity, and then letting them go when they were ready to drift again. The solid and the liquid, the earth and the ocean, work together in harmony, creating conditions that neither alone could have achieved. Experiments in modern laboratories have offered glimpses of this process. When simple organic molecules are placed in solutions with clays or metal sulfides, they often form longer chains, more easily than in plain water. When lipids are introduced, they sometimes gather on mineral surfaces into layers resembling membranes, the precursors of cell walls. These findings suggest that minerals did not merely provide a backdrop but actively encouraged organization, helping to bridge the gap between scattered molecules and coherent systems. The importance of surfaces also extends to cycles of drying and wetting. On early Earth, in tidal pools, or along volcanic shores, water may have evaporated during the day, leaving molecules concentrated on mineral grains. At night, or when tides returned, the water would cover them again, allowing reactions to proceed. These cycles, repeated endlessly, could have driven the gradual accumulation of complexity. Each drying phase pressed molecules closer together. Each wetting phase allowed them to interact and reorganize. Over time, these rhythms may have woven the first steps toward life. If we pause to reflect, we can see how natural and unforced this vision. Island life did not need extraordinary conditions, only the patient interplay of water, energy, and stone. The Earth's crust, in all its quiet solidity, was part of the story from the beginning. Each mineral grain, each fragment of clay, each surface of iron sulfide was a participant in the drama, holding and shaping the molecules that would eventually awaken into life. There is something humbling in this thought. The ground beneath our feet, the rocks and soils we often take for granted, carry within them a history of participation in life's earliest moments. They were not alive, yet they were essential to life's birth. They remind us that the boundary between the living and the non-living is not a sharp divide, but a gentle gradient, where chemistry and geology blend into biology. As you listen and drift into rest, imagine a quiet shoreline on the ancient earth. Pools of water shimmer under a dim sun, their surfaces rippling with the wind. Within these pools, grains of clay glisten, their layers trapping molecules like pages of an unwritten book. Along the seafloor, mineral chimneys rise, their porous walls filled with chambers of warmth and chemistry. In these silent places, molecules gather, meet, and linger, guided by the subtle patterns of minerals. It is not yet life, but it is something close, something preparing the way. And so, in this part of our journey, we see that the origins of life may not have depended solely on oceans and energy, but also on the quiet work of minerals and surfaces. They offered structure, concentration, and protection, turning scattered molecules into systems that could persist. In the next part, we will turn to the idea of the RNA world, a vision of early life in which a single molecule carried both information and function, perhaps becoming the first true bridge between chemistry and biology. 10. The RNA world hypothesis. As we move further into the story of life's origins, we begin to encounter ideas that bring us closer to the threshold between chemistry and biology. Among these ideas, one stands out as both elegant and persuasive, often referred to as the RNA world hypothesis. It is the vision that before DNA and proteins, before cells and organisms, there was a simpler stage where RNA, a molecule we know well today, played the starring role. RNA, or ribonucleic acid, is familiar to us as the messenger that carries genetic instructions from DNA to the machinery that builds proteins. Yet it is also capable of more. Unlike DNA, which is stable but inert, RNA can fold into shapes that allow it to catalyze reactions, acting like a primitive enzyme. This dual nature, able to store information and to perform chemical tasks, makes RNA a plausible candidate for the first molecule that could bridge the gap between lifeless chemistry and the beginnings of life. To appreciate why RNA is such a compelling idea, it helps to consider the functions it performs in modern cells. DNA is the long-term library of genetic information, but DNA does not act on its own. To build proteins, cells transcribe DNA into RNA, and this RNA carries the instructions to ribosomes, the molecular machines that assemble amino acids into chains. Some RNA molecules, however, do more than act as messengers. Certain forms of RNA fold into intricate shapes and act as catalysts, speeding up chemical reactions in the cell. These catalytic RNAs are known as ribozymes. Their existence shows that RNA is not just a passive courier of information, but also an active participant in the chemistry of life. This dual ability, rare among molecules, suggests that in an earlier, simpler world, RNA might have been both the keeper of information and the worker that carried out reactions. The idea of an RNA world is appealing because it offers a way to solve what is sometimes called the chicken and egg problem of life. In modern biology, DNA stores instructions, but it requires proteins to copy and express those instructions. Proteins, in turn, require DNA to know how to build themselves. Which came first, DNA or proteins? The RNA world hypothesis suggests that neither did. Instead, RNA came first, serving as both gene and enzyme, both instruction and tool. Over time, proteins emerged as more efficient catalysts, and DNA as a more stable store of information. But both may have evolved from an earlier stage dominated by RNA. It is soothing to think of RNA not as a sudden invention, but as the natural outgrowth of the chemistry of the early Earth. Nucleotides, the building blocks of RNA, can form under plausible prebiotic conditions, especially with the help of minerals and cycles of drying and wetting. Once present, these nucleotides can link into chains, forming short strands of RNA. Experiments in laboratories have shown that under the right conditions, RNA strands can copy portions of themselves, or at least encourage other RNA strands to form complementary sequences. Though imperfect, these processes hint at the possibility of self-replication, the essential property of life. Once molecules can make copies of themselves, even imperfect ones, natural selection can begin to act, favoring sequences that copy more effectively or survive more reliably. Ribozymes, discovered in the 1980s, gave new strength to the RNA world hypothesis. Until then, enzymes were thought to be made only of proteins, with their complex folding and diverse side chains. The discovery that RNA itself could catalyze reactions was a revelation. It showed that RNA could, in principle, sustain a system of both heredity and metabolism. Some ribozymes are able to join nucleotides together, others can cut RNA strands, and still others are central to the ribosome, the ancient machine that builds proteins in every living cell. This last fact is particularly striking, At the heart of the ribosome, where amino acids are linked together to form proteins, the catalyst is not a protein but RNA. This suggests that proteins themselves may have arisen in a world already shaped and guided by RNA. The RNA world hypothesis does not claim that RNA appeared fully formed or that it alone created life. Rather, it suggests that RNA was a central stage in a gradual process. Before RNA, there may have been even simpler molecules that carried information imperfectly. After RNA, DNA and proteins took over much of its role. But RNA remains deeply embedded in biology, a living fossil of an earlier era. Every time a cell transcribes DNA into RNA, every time RNA guides the assembly of proteins, we see echoes of that ancient world. There are, of course, challenges to the hypothesis. RNA is less stable than DNA, prone to breaking down in water or under heat. The spontaneous formation of long RNA strands from nucleotides is difficult, and the process of replication is far from perfect without the help of proteins. Yet these challenges are not insurmountable. In natural settings, minerals could have stabilized RNA, and cycles of concentration could have encouraged longer strands. Imperfect replication, while fragile, still allows evolution to occur, because variation is the raw material of natural selection. What matters is not perfection but persistence, and RNA has shown itself capable of both. The vision of an RNA world is not only scientific but also poetic. It invites us to imagine an ancient Earth not yet filled with organisms, but already humming with the quiet activity of molecules. Strands of RNA drifted in shallow pools or nestled within mineral pores, folding into shapes, copying fragments of themselves, breaking and reforming, enduring just long enough to try again. There was no intention, no awareness, only the patience of chemistry exploring possibility. And yet, from this patience, a new kind of order arose, one that could preserve information across generations of molecules. In those faint steps, we see the outline of life itself. As you reflect on this, imagine looking down at an ancient shoreline, the tide pools shimmering with water rich in organic compounds. Within them, invisible to the eye, chains of RNA assemble and rearrange. Some fold into knots that do nothing, others collapse and vanish, but a few fold in ways that let them act. These few endure longer, and among them, some can help other strands form. Slowly, across ages of time, these tiny differences accumulate, and what was once random begins to show persistence. The pools become workshops, where molecules write and rewrite themselves, each attempt a step closer to the bridge from chemistry to biology. The RNA world hypothesis may never be proven in full, for we cannot return to those ancient days to watch it unfold. But the evidence we hold today, ribozymes, the central role of RNA in cells, the plausibility of nucleotide formation, offers a strong case. It reminds us that life need not have begun with complexity, but with something simple, yet versatile, a molecule capable of carrying both memory and function. RNA, in its duality, seems uniquely suited to this role, and perhaps it truly was the first great actor on the stage of life. As this part draws to a close, we may rest with the thought that within our own cells, RNA still whispers of this ancient world. Every messenger RNA, every catalytic RNA, every ribosome at work carries echoes of a time long before DNA ruled, long before proteins built their diverse forms. In the next part of our journey, we will consider not just the molecules themselves, but how surfaces and enclosures may have shaped them into protocells, small containers that offered the first glimpse of what we now recognize as the living cell. 11. Self-replication and information. One of the most profound steps in the origin of life was the emergence of self-replication, the ability of molecules not only to exist but to make copies of themselves. This is the quiet threshold where chemistry becomes something more, where fleeting arrangements of atoms cross into persistence, carrying their own patterns forward through time. In essence, life is a story of information, of instructions written in molecules, copied and handed down through countless generations. Without replication, molecules would appear and disappear, created by chance reactions and lost just as quickly. With replication, patterns endure, and once they endure, they can be shaped by natural selection. This moment, when molecules first gain the power to reproduce themselves, marks one of the most delicate yet transformative events in Earth's history. To understand self-replication, we must first think about information. Information, in this context, does not mean words on a page or thoughts in a mind. It means a sequence, an arrangement of parts that carries meaning because it can be copied and used. A strand of RNA or DNA is made up of nucleotides, small building blocks linked into chains. The order of these nucleotides forms a code, a pattern that can guide the building of proteins or, more fundamentally, the copying of itself. In this way, molecules carry instructions, not consciously, but through the natural consequences of their structure. The power of information lies in its repeatability. Once a sequence exists, it can be preserved, passed on, and altered only slightly, allowing continuity with variation. In the early Earth, the first replicating molecules may not have been as sophisticated as modern DNA or RNA. They may have been shorter strands, or even different molecules altogether, capable of only rough copying. Experiments in laboratories suggest that under the right conditions, small RNA molecules can encourage the formation of complementary sequences, strands that align with their bases and assemble into copies. The process is not perfect, but perfection is not required. Even imperfect replication is enough to start the process of evolution, because errors create variation, and variation is the material upon which natural selection acts. Some strands survive longer, some copy faster, and over time, those with even slight advantages become more common. The emergence of replication also brings with it the idea of heredity. For life as we know it, heredity is the faithful passing down of information from one generation to the next. In humans, this means the inheritance of DNA from parents to children. In the earliest world of molecules, it meant that certain sequences were more likely to give rise to similar sequences. This continuity allowed patterns to persist not just for moments, but across ages. Imagine a pool of molecules where new chains are forming constantly, most of them breaking apart within hours or days. Among them, one particular sequence has the ability to encourage the making of copies. That sequence, unlike the others, begins to spread, not because it has intention, but because its structure naturally favors persistence. In this way, heredity was born, a fragile thread that would eventually be woven into the vast tapestry of life. Replication also implies competition, though in the gentlest sense, molecules that replicate more effectively will, over time, become more numerous than those that do not. The pool of ingredients is limited, so molecules that can secure those ingredients and use them for copying will gradually dominate. This is the earliest form of natural selection, long before there were organisms, eyes, wings, or brains. Selection acted on molecules, favoring those that could endure and reproduce. In this way, the seeds of evolution were sown, not with animals or plants, but with chains of nucleotides drifting in ancient waters. It is soothing to think of this process not as a sudden event, but as a slow unfolding. There was no moment when chemistry stopped and life began, but rather a gradual blending, a soft gradient across which molecules grew more capable of copying themselves, more capable of persisting. Each small improvement was preserved, not because of foresight, but because copying naturally favors stability. Over millions of years, what began as fragile chains became more robust, and replication became the central rhythm of life. Modern biology still bears the marks of this ancient origin. Every living cell on Earth today depends on replication. DNA is copied when cells divide, ensuring that each new cell carries the same instructions. RNA is copied when proteins are made, ensuring that the right sequences are expressed at the right time. Even viruses, though they depend on host cells, rely on replication to persist. At every level of biology, from the smallest bacterium to the most complex human, the ability to copy information is the foundation. This universality suggests that replication is not a late invention, but one of the earliest and most fundamental features of life. There are mysteries, of course, in how replication first arose. Nucleotides themselves are complex, and forming long chains in natural conditions is not straightforward. Some scientists suggest that mineral surfaces helped align them, encouraging bonds. Others propose that cycles of wetting and drying concentrated nucleotides enough to link them together. However, it happened. Once even a simple replicating system was established, the door was open. Complexity could follow, driven not by chance alone, but by the steady guidance of selection. It is humbling to reflect on how much of life's beauty and diversity flows from this simple principle. Replication means continuity, and continuity means the accumulation of changes. Each error in copying is a mutation, most insignificant, some harmful, but a few beneficial. Across vast spans of time, these small differences accumulate, producing the variety of forms we see in the living world. From the first replicating molecules came all of evolution, all of adaptation, all of the endless creativity of life. The elegance of this process lies in its simplicity. To copy is to persist, and to persist is to be shaped by the world. As you drift with these thoughts, imagine again the ancient Earth, its oceans rich with molecules. In one corner of a tidal pool, a strand of RNA forms, fragile and fleeting. By chance, it folds in a way that allows it to help other strands assemble. This one small property makes it more likely to persist, and so copies of it appear, uneven, but sufficient. Across thousands of years, this sequence spreads, not because it knows how, but because its structure allows it. In this quiet process, replication begins, and with it, information takes root. The pool becomes not just a random mix of molecules, but a place where patterns endure, a place where the first faint threads of heredity are woven. The story of self-replication is the story of how memory entered chemistry. It is the moment when molecules began to carry not only form but instruction, when the past could shape the future through the preservation of patterns. It is the foundation of all that would follow: metabolism, cells, organisms, ecosystems, and consciousness. Without replication, there is no continuity, no inheritance, no evolution. With it, the story of life unfolds, step by step, across billions of years. As this part closes, let us hold to the image of molecules carrying information forward, like whispers passed from one generation to the next. Fragile though they were, they endured, and in their endurance, they gave rise to everything alive today. In the next part, we will turn to the idea of protocells, the simple enclosures that may have sheltered these replicating molecules, offering them a space to interact, to persist, and to take another step closer to what we now recognize as the living cell. 12. The emergence of protocells. As we move deeper into the story of life's origins, we begin to approach one of the most critical transitions, the step from free-floating molecules to enclosed systems. Molecules alone, even replicating ones, drifted in the waters of the young earth, subject to dilution, destruction, and dispersal. They could copy themselves, but they lacked boundaries, and without boundaries, there could be no true individuality, no separation between inside and outside. and no way to maintain stability against the shifting tides of the environment. The emergence of protocells, small, simple enclosures of molecules within thin walls, offered a solution. These primitive containers provided shelter, allowed concentration of ingredients, and set the stage for the eventual rise of true cells. In these protocells, we may see the earliest forms of something that begins to look familiar to us. The first outlines of life as a contained, self-sustaining system. A protocell can be imagined as a bubble, a small sphere formed by lipids, the molecules that make up modern cell membranes. Lipids are remarkable in their dual nature. One end of the molecule is drawn to water, while the other repels it. When placed in water, lipids spontaneously arrange themselves so that the water-loving ends face outward and the water-fearing ends cluster inward. This arrangement forms a bilayer, a thin sheet that naturally curves into a sphere, enclosing a pocket of water within. In this simple way, without any guiding hand, lipids create membranes. These membranes are not alive, but they have a crucial property. They can hold other molecules inside, separating them from the outside world. In doing so, they create a tiny interior space, a protected environment where chemistry can persist. On the early Earth, lipids may have formed from reactions in the atmosphere, from volcanic activity, or from compounds delivered by meteorites. Experiments have shown that when fatty acids and other simple lipids are placed in water, they readily assemble into vesicles, small bubbles resembling protocells. These vesicles can trap nucleotides, amino acids, or other molecules inside. If the vesicle grows too large, it may divide, splitting into two smaller bubbles, each carrying some of the contents of the original. In this way, protocells show behaviors that hint at life, division, and inheritance of contents, even though they are entirely the result of chemistry. The importance of protocells lies in the concentration they provide. In the vastness of the oceans, molecules are scattered, and reactions occur slowly. Within the walls of a protocell, molecules are brought together in higher concentration, increasing the chances of interaction. Replicating RNA strands, for example, would benefit greatly from being enclosed, shielded from dilution and degradation. Inside a protocell, they could persist longer and copy themselves more effectively. In this sense, protocells may have acted as incubators, nurturing fragile chemistry and giving it time to refine itself into something more robust. Another advantage of protocells is the establishment of an inside and an outside. Modern cells depend on this distinction, maintaining internal conditions very different from their surroundings. Protocells, though simple, already hint at this ability. Their membranes allow some molecules to pass through while excluding others. This selectivity is imperfect, but even a partial barrier creates the possibility of homeostasis, the maintenance of stable internal conditions. Within protocells, molecules could accumulate without being immediately lost, creating microenvironments different from the ocean outside. These microenvironments were the first step toward individuality, the first suggestion that systems could exist as entities, not just as scattered reactions. Protocells also offer a framework for the cooperation of molecules. Replicating RNA, catalytic ribozymes, and metabolic reactions could all occur more effectively within the same enclosure. Over time, protocells that captured useful combinations of molecules would persist longer than those that did not. In this way, protocells became the stage for a new kind of selection. No longer were individual molecules alone in their struggle for persistence. Now, groups of molecules enclosed together could act as units, with their survival depending on the harmony of their interactions. This communal persistence is a hallmark of true life, and protocells may have been the first to embody it. It is soothing to imagine how natural this process might have been. No special event was required, no sudden leap. Lipids self-assemble in water, forming vesicles spontaneously. Molecules are trapped inside by chance, Some vesicles divide under stress, creating smaller ones. Over time, vesicles that happen to enclose, replicating RNA or catalytic molecules, persist longer, divide more effectively, and spread. Each cycle repeats, driven not by intent but by the quiet logic of chemistry. Through these simple steps, protocells become more stable, more capable, and more lifelike. Laboratory studies have shown that protocells can even compete in primitive ways. Vesicles that grow larger by incorporating more lipids can divide more often, outnumbering smaller ones. Vesicles that capture certain molecules may become more stable, resisting rupture. In this way, protocells provide a platform for evolution. They are not alive in the full sense, but they offer the necessary framework for life to begin evolving. Once enclosed, molecules can be passed on from generation to generation of protocells, and with this inheritance, variation and selection begin to act on a new level. The emergence of protocells also helps to explain the transition from an RNA world to the modern cell. RNA alone, floating in the ocean, could replicate but remained vulnerable. Within protocells, RNA gained protection, and with it, the opportunity to interact with proteins as they began to emerge. The combination of RNA, proteins, and lipids within protocells may have been the bridge to the first true cells, where these components became inseparably linked. DNA later joined the system as a more stable genetic material, but by then the framework of life membranes, heredity, metabolism was already in place. As you listen, imagine the ancient seas filled not only with drifting molecules but with countless tiny bubbles, invisible to the naked eye, each one a little world unto itself. Some are empty, filled only with water. Others contain random molecules, inert and fleeting. But a few, by chance, hold replicating RNA, catalytic ribozymes, or useful enzymes. These few begin to persist, their membranes protecting fragile chemistry, their divisions passing contents forward. With each cycle, the oceans become richer in protocells, until at last the line between chemistry and life blurs almost completely. There is a quiet wonder in knowing that something as simple as a bubble could have played such a vital role in the story of life. We see bubbles today in foaming waves, in boiling springs, in soap lather, and in each one we can glimpse a reminder of those earliest enclosures. Life, in all its complexity, may trace its origins to structures no more complicated than tiny vesicles of lipids, floating gently in water. They were the first rooms of life, the first shelters, the first boundaries between self and world. As this part of the journey closes, we may rest with the thought that protocells were not merely containers, but the cradles in which life's earliest systems were nurtured. They gave molecules stability, identity, and continuity, preparing the way for the true cells that would eventually inherit the earth. In the next part, we will consider how these protocells gave rise to the first microbes, the earliest organisms that we can truly call living, and how they began to shape the planet in ways still felt today. 13. When we speak of the first microbes, we arrive at a moment in the story of life where chemistry has at last become biology. Protocells, with their simple membranes and captured molecules, had provided the framework, but the leap to living organisms required more than enclosure. It required the integration of replication, metabolism, and heredity into systems that could endure, adapt, and spread. In the quiet depths of Earth's oceans, perhaps around hydrothermal vents, perhaps in shallow pools warmed by the sun, the first true cells emerged. These were microbes, tiny, single-celled organisms that carried within them the essential features of life as we still define it today. In their simplicity, they set the stage for everything that would follow, for every tree and bird, every fish and mammal, every human being. All of us trace our ancestry back to these earliest microbial pioneers. The first microbes were likely prokaryotic in form. Unlike the complex cells of plants and animals today, prokaryotes have no nucleus, no internal compartments, only a membrane enclosing genetic material and the machinery of metabolism. Yet within that simplicity lies elegance. A single cell could take in nutrients from its surroundings, process energy, grow, and divide. It could maintain homeostasis, keeping its inner environment distinct from the outer world. Most importantly, it could reproduce, passing along genetic information to its offspring. With these abilities, the first microbes were not merely collections of molecules but living beings, capable of continuity and change. What did these first microbes look like? We cannot know for certain, but they were likely small, perhaps only a few micrometers in size, invisible to the naked eye. Their membranes were made of simple lipids, not yet as specialized as those of modern cells. Their genetic material was probably RNA at first, later joined or replaced by DNA as a more stable store of information. Their metabolism may have been primitive, relying on chemical reactions powered by the environment around them. Some may have harvested energy from hydrogen and carbon dioxide, others from sulfur compounds, abundant near vents. In their diversity, they explored the many ways that life can draw energy from its surroundings, testing possibilities that would later be refined and expanded. The fossil record provides tantalizing glimpses of these early microbes. In rocks more than 3.5 billion years old, scientists have found microscopic structures resembling cells, as well as chemical signatures that suggest biological activity. Stromatolites, layered formations built by microbial communities, appear in rocks of similar age. These layered structures form when microbes trap and bind sediments, creating mounds that grow over time. Modern stromatolites still exist in a few places on Earth, and they give us a living connection to those ancient communities. Though the individual microbes are long gone, their collective handiwork remains, a testament to their persistence. The earliest microbes were also the architects of Earth's environment. By consuming and releasing chemicals, they altered the composition of the oceans and the atmosphere. Microbes that performed photosynthesis, using sunlight to build sugars from carbon dioxide and water, began to release oxygen as a byproduct. At first, this oxygen reacted with iron in the oceans, creating bands of rust-colored rock that we still see in ancient formations today. But over time, oxygen accumulated in the atmosphere, leading to the Great Oxygenation Event, a turning point that transformed Earth's chemistry and made possible the evolution of more complex life. All of this began with microbes, quietly altering their world through their daily existence. It is soothing to reflect on how humble these beginnings were. The first microbes had no eyes, no limbs, no awareness as we know it. They were tiny, fragile cells, floating in water, dividing when they could, surviving when conditions allowed. Yet from these quiet lives came the foundation of all future life. They established the basic principles of biology: metabolism to harness energy, heredity to preserve information, and evolution to shape form and function over time. Each division was a continuation of life, each mutation a chance for something new. Slowly, across billions of years, these small changes accumulated, and the diversity of life began to unfold. Microbes also remind us that complexity is not always necessary for success. Even today, prokaryotes dominate the earth in number and diversity. They live in soil, in water, in the air, and even within the bodies of other organisms. They thrive in conditions that would destroy other life-boiling springs: acidic lakes, frozen tundra, deep within rocks. Their resilience is unmatched, and it reflects the ancient roots of their design. The first microbes were not stepping stones to something greater. They were, and remain, a successful form of life in their own right. Every tree and animal that came later owes its existence to them, but they themselves continue to flourish independently, as they always have. To picture the first microbes is to imagine an ocean teeming with invisible life. At first glance, the water may have seemed empty, but within it, countless cells floated, dividing and multiplying. Some clustered together in communities, forming mats on rocks or sediments. Others drifted alone, carried by currents. Each cell was a tiny world, a system of molecules working in harmony, maintaining itself against the pull of entropy. Though they lacked consciousness, their persistence was its own form of purpose: to endure, to replicate, to continue. It is humbling to think that all the complexity of the living world, forests, coral reefs, the flight of birds, the thought of humans arises from principles first embodied in these simple microbes. The patterns of replication, metabolism, and selection that began with them have never ceased, only grown more elaborate. In every heartbeat, in every breath, in every cycle of cell division in our own bodies, we replay the same rhythms that began billions of years ago. The continuity is unbroken, a chain stretching back to those first fragile cells. As you rest with these thoughts, imagine the patience of time itself. Billions of years passed while microbes ruled the earth alone. No plants, no animals, no forests or insects, only oceans filled with single-celled life. To us, this might seem like emptiness, but in truth, it was richness beyond measure. The earth was alive, filled with countless beings, each a continuation of the first spark. It was during this long age that the groundwork was laid for everything to come. The microbes shaped the planet, altered the air, and paved the way for complexity. Their reign was not a prelude, but a profound and enduring chapter in the story of life. And so, in this part of our journey, we see the arrival of true organisms, microbes, the first living beings, in the full sense of the word. They carried within them the essential features of life, features that persist in every cell today. They remind us that life began not in grandeur but in simplicity, not in sudden leaps but in steady steps. In the next part, we will turn to one of the greatest transformations wrought by these tiny organisms, the rise of photosynthesis and the release of oxygen, a process that would change the world forever. 14. Photosynthesis. In the story of life on Earth, there are few chapters as transformative as the rise of photosynthesis. With this quiet innovation, tiny microbes learn to capture sunlight and use it to build energy-rich molecules, releasing oxygen as a byproduct. It was not a sudden invention, but a gradual unfolding, shaped by countless generations of microscopic life. Yet the impact of photosynthesis was vast. It altered the chemistry of the oceans. It filled the skies with oxygen, and it laid the foundation for all complex organisms that would follow. To reflect on this event is to recognize that the atmosphere we breathe today, the very air that sustains us, is a legacy of those ancient microbes who first turned sunlight into food. At its heart, photosynthesis is a simple process. Light from the sun strikes pigments within cells, pigments capable of absorbing energy. This energy is then used to drive chemical reactions that convert carbon dioxide and water into sugars. In modern organisms, these sugars provide the energy and building blocks needed for growth and reproduction. The process also produces oxygen, released as a byproduct. For us, oxygen is essential, fueling the respiration that powers our bodies. For the earliest Earth, however, oxygen was a novelty, an element not yet abundant in the air or seas. The appearance of oxygen marked a profound change, one that reshaped the entire planet. The earliest forms of photosynthesis may not have released oxygen at all. Some microbes likely used light to extract energy from compounds such as hydrogen sulfide, producing sulfur instead of oxygen. This form of anoxygenic photosynthesis still exists today in certain bacteria. It was a useful strategy, allowing organisms to harvest sunlight even in environments rich in sulfur, such as near volcanic vents. But over time, a new form of photosynthesis emerged, one that used water as the source of electrons. In splitting water, these microbes released oxygen. This innovation, carried out by ancestors of cyanobacteria, was the beginning of what we now call oxygenic photosynthesis. Cyanobacteria are among the most significant organisms in Earth's history. Though small and simple, they possessed the remarkable ability to capture sunlight efficiently and to release oxygen into the environment. They formed colonies and mats, sometimes building layered structures known as stromatolites. These microbial communities thrived in shallow waters, spreading across coastlines and lagoons. As they grew and divided, they exhaled oxygen into their surroundings, slowly changing the chemistry of the oceans and, eventually, the atmosphere. For millions of years, the oxygen they produced was absorbed by minerals, reacting with iron in the seas to form rust-colored deposits. These banded iron formations, still visible in ancient rocks today, are evidence of the slow accumulation of oxygen in Earth's waters. Eventually, the supply of reactive minerals was exhausted, and oxygen began to accumulate in the atmosphere. This turning point, known as the Great Oxygenation Event, occurred more than 2 billion years ago. It was one of the most dramatic transformations in the history of the planet. Before this event, the atmosphere contained little to no oxygen, and life consisted only of anaerobic microbes that thrived without it. Afterward, oxygen became a permanent feature of the air, paving the way for aerobic respiration, a far more efficient way of extracting energy from food. For many organisms, oxygen was toxic, and the rise of oxygen brought extinctions. But for others, it was an opportunity, opening new pathways of metabolism and complexity. It is soothing to think of this transformation not as an abrupt catastrophe, but as a gradual shift, stretched across millions of years. Day after day, tiny microbes captured sunlight, built sugars, and released oxygen, each cell unaware of the global changes it was helping to bring about. Their collective labor reshaped the skies, filling them with a gas that would one day sustain forests, animals, and human beings. The oxygen they released also created the ozone layer, a shield that absorbed harmful ultraviolet radiation, making Earth's surface more hospitable for life. Step by patient step, photosynthesis prepared the stage for the diversity we now see. Even now, photosynthesis remains the foundation of life. Plants, algae, and cyanobacteria continue to capture sunlight, forming the base of nearly every food chain. The oxygen we breathe each moment is the gift of photosynthesis, a reminder of its enduring power. It connects us to those ancient microbes, whose quiet persistence changed the world forever. Every breath we take is an echo of their work, every leaf that unfurls a continuation of their innovation. To imagine this transformation, picture the ancient seas shimmering under a dimmer Sunday. Floating within them are countless cells of cyanobacteria, small spheres drifting in colonies. As light strikes them, they stir with energy, splitting water, building sugars, releasing tiny bubbles of oxygen. At first, these bubbles vanish into the water, absorbed by iron and other minerals. The oceans turn red with rust, layer upon layer, settling onto the seafloor. Over time, the minerals can no longer absorb it all, and oxygen escapes into the air. Slowly, invisibly, the atmosphere changes, its composition shifting with each passing age. What began as bubbles in the sea becomes a sky filled with oxygen, blue and clear, ready to sustain new kinds of life. The Great Oxygenation Event was not only a chemical transformation, but an evolutionary one. With oxygen available, new metabolisms arose. Aerobic respiration allowed organisms to extract far more energy from food than anaerobic methods. This abundance of energy made greater complexity possible. Cells could grow larger, build more intricate machinery, and eventually form partnerships that gave rise to eukaryotes, the ancestors of plants and animals. In this way, photosynthesis was the hidden engine that drove the rise of complexity, long before the first animals walked the earth. Yet even as it enabled new life, oxygen also posed challenges. For many ancient microbes, oxygen was poisonous, damaging their delicate molecules. Some retreated to anaerobic niches, environments where oxygen could not reach, such as deep sediments or underground aquifers. Others adapted, developing enzymes to protect themselves from oxygen's reactive nature. This adaptation itself was a driver of evolution, pushing life into new forms and strategies. The story of photosynthesis is therefore one of both creation and challenge, of opportunities gained and losses endured. As we rest with these thoughts, it is humbling to realize that the world we inhabit today, its breathable air, its protective ozone, its rich ecosystems, is the legacy of microbial activity billions of years ago. Life transformed its own planet, turning a barren world into one filled with possibility. The first microbes that captured sunlight could not have foreseen the outcome, yet their persistence created conditions that made everything else possible. And so, the rise of photosynthesis and the release of oxygen mark a turning point in the history of life. It was the moment when the planet itself was reshaped by biology, when the actions of tiny cells began to influence the global environment. From that moment onward, life and Earth would be inseparable, each shaping the other in an endless dance. In the next part of our journey, we will explore more deeply the great oxygenation event itself, a time when the slow work of microbes transformed the air and set the stage for the expansion of life into new and extraordinary forms. 15. The Great Oxygenation Event. The Great Oxygenation Event, sometimes called the oxygen catastrophe or the oxygen revolution, was one of the most profound turning points in the history of Earth. It marked the time when oxygen, once almost absent from the atmosphere, began to accumulate in significant amounts, forever changing the chemistry of the planet and the trajectory of life. To think of this event is to imagine not a sudden explosion, but a gradual unfolding, a long and patient transformation carried out by countless tiny microbes, each one contributing in its own small way. Over millions of years, their collective work reshaped oceans, skies, and rocks, leaving a legacy that remains with us in every breath we take. Before this event, Earth's atmosphere was very different from the one we know. It was rich in gases like methane, carbon dioxide, and nitrogen, but oxygen was scarce. For the earliest forms of life, this was not a problem. They were anaerobic, meaning they lived and thrived without oxygen, often using chemical reactions with sulfur, hydrogen, or iron to power their metabolisms. In such an environment, oxygen was not a necessity, it was irrelevant. But with the emergence of cyanobacteria and the innovation of oxygenic photosynthesis, oxygen began to appear as a byproduct of their daily activity. These microbes captured sunlight, split water molecules, and built sugars for their survival, releasing oxygen as waste. At first, the oxygen they produced vanished almost immediately, reacting with dissolved iron in the oceans or with gases in the atmosphere. It was absorbed, bound up, and hidden away. Yet the cyanobacteria persisted, producing more oxygen with every division, every colony, every layer of microbial mat. For millions of years, the oxygen released was captured by iron. In the oceans, iron dissolved in the water reacted with oxygen to form rust, or iron oxides, which settled onto the seafloor in alternating bands. These banded iron formations, still visible in ancient rocks, are silent witnesses of that time, a geological record of the gradual buildup of oxygen. Each band tells of a cycle: oxygen produced, iron consumed, layers of rust forming. Slowly, the oceans became depleted of free iron. Once the iron was bound up, oxygen had fewer sinks to absorb it, and it began to accumulate in the water and then in the air. The rise of oxygen was both a blessing and a challenge. For organisms that could use oxygen, it offered enormous advantages. Oxygen allowed for aerobic respiration, a process far more efficient at extracting energy from food than anaerobic methods. With this new metabolic pathway, cells could harvest much more energy, supporting larger size, more complexity, and greater diversity of functions. The groundwork was laid for the eventual rise of complex, multicellular life. For many other organisms, however, oxygen was toxic. Oxygen is highly reactive, and it can damage delicate molecules like proteins, lipids, and nucleic acids. For microbes that had evolved in an oxygen-free world, exposure to oxygen was deadly. Many of them perished as oxygen levels rose, unable to adapt to the new conditions. Others retreated into anaerobic environments, where oxygen could not reach: deep sediments, underground aquifers, or within the bodies of other organisms. Even today, anaerobic microbes still exist in such places, living reminders of a time before oxygen filled the skies. The accumulation of oxygen also transformed the Earth's geology and atmosphere in ways beyond biology. Methane, once a dominant greenhouse gas in the atmosphere, was broken down by oxygen, weakening the greenhouse effect and possibly triggering global cooling events. Some scientists believe that the rise of oxygen contributed to the first known snowball Earth, a period when ice spread across much of the planet. Whether directly responsible or not, the timing suggests that the oxygen revolution and dramatic climate shifts were linked. Oxygen, in this sense, reshaped not only life, but also the physical state of the planet. Over time, oxygen levels stabilized, reaching levels that could support new forms of life. One of the most significant outcomes of the Great Oxygenation event was the formation of the ozone layer. As oxygen accumulated in the upper atmosphere, some of it transformed into ozone, a molecule that absorbs harmful ultraviolet radiation from the sunday. This protective layer allowed life to explore new habitats closer to the surface and eventually on land, shielded from radiation that had once been deadly. In this way, oxygen not only changed the chemistry of the air but also extended the possibilities of life's reach. It is humbling to reflect on how slow and patient this process was. The Great Oxygenation event took place over hundreds of millions of years, a span of time so vast that it is difficult for us to grasp. Day after day, countless microbes carried out photosynthesis, releasing tiny bubbles of oxygen. Each bubble was insignificant by itself, but together, across eons, they transformed the planet. It was not intention or design, but persistence, the quiet persistence of life, multiplying and dividing, always reaching for survival, that reshaped Earth into a place where animals, plants, and eventually humans could exist. To picture this transformation, imagine the ancient seas glowing with microbial mats, green with cyanobacteria. As the sun rises, they stir with energy, capturing light and releasing oxygen. Invisible bubbles rise from the water, merging with others, until the air itself begins to change. Slowly, the skies clear, the haze of methane diminishing, the blue of oxygen-rich air emerging. The oceans, once rich with iron, now turn clearer as rust settles to the seafloor. What was once a world without oxygen becomes a world defined by it, a transformation so complete that it is hard for us now to imagine a time before. Even today, The legacy of the great oxygenation event surrounds us. The iron formations in ancient rocks, the oxygen in every breath, the ozone above protecting us all, are echoes of that ancient revolution. In every cell of our bodies, mitochondria consume oxygen to produce energy, a process made possible only because cyanobacteria once began to release oxygen billions of years ago. We carry their legacy within us, in our respiration, in our dependence on oxygen, in the very possibility of our existence. As you rest with these thoughts, it is calming to remember that even the most profound changes often come from the smallest actions, repeated over time. The great oxygenation event was not the result of a sudden catastrophe or a single moment of invention. It was the collective work of countless microbes, each one simple, each one unaware, but together, reshaping a planet. It is a reminder of the quiet power of persistence, of how life shapes its world not through force, but through continuity. And so, the Great Oxygenation Event stands as one of the most important transitions in Earth's history. It brought challenges and extinctions, but it also opened doors to complexity and abundance. It turned Earth into a planet where oxygen breathers could thrive, where new forms of life could flourish, and where the foundations for animals and plants were laid. In the next part of our journey, we will turn to alternative theories of life's origins, including the intriguing idea of panspermia, the possibility that life seeds may have come not from Earth alone but from the wider cosmos. 16. Alternative theories, panspermia. As we reflect on the possible beginnings of life, most visions keep our gaze firmly on Earth, the primordial soup enriched by lightning, the hydrothermal vents releasing mineral-rich fluids, the protocells forming along ancient shorelines. Yet, there is another idea, one that extends our imagination beyond the planet itself, reaching outward into the wider cosmos. This is the theory of panspermia, the suggestion that life, or at least its ingredients, may not have originated here alone but may have arrived from elsewhere, carried across the dark spaces between worlds. The word itself means seeds everywhere, and it captures a simple but profound thought. Perhaps the seeds of life are not unique to Earth, but scattered throughout the universe, waiting only for a suitable home in which to grow. The idea of panspermia is not new. Ancient thinkers, long before the rise of modern science, speculated that life might be universal, spread across the heavens. In modern times, the theory has taken on more specific forms, rooted in astronomy, chemistry, and biology. It does not necessarily suggest that living organisms traveled through space intact, though some versions do. More often, it imagines that the basic building blocks of life, amino acids, nucleotides, sugars, or lipids could have been formed elsewhere, perhaps in interstellar clouds or on comets, and then delivered to Earth by meteorites or other celestial bodies. If so, then the origins of life may be both earthly and cosmic, shaped by local conditions but seeded by materials from afar. Evidence for panspermia rests in part on the chemistry of space itself. Observations of interstellar clouds have revealed the presence of organic molecules, including amino acids and simple sugars. These molecules form naturally in the cold depths of space, where dust grains coated with ices are exposed to radiation, sparking chemical reactions. When comets and asteroids condense from such material, they carry these molecules with them. Indeed, analyses of meteorites that have fallen to Earth have revealed amino acids and other organic compounds, some with patterns distinct from those produced by terrestrial biology. These findings suggest that the ingredients of life are not confined to Earth, but are widespread, forming wherever conditions allow. Comets, in particular, are often considered possible carriers of life seeds. Made of ice, rock, and organic compounds, they spend much of their time in the cold outer regions of the solar system, preserving fragile molecules for billions of years. When they are perturbed by gravity and fall inward, they can collide with planets, delivering their contents. It is thought that comets may have supplied much of Earth's water, and if they carried water, they likely carried organics as well. The bombardment of the young Earth by comets and asteroids may thus have enriched its oceans not only with water but with a vast library of chemical possibilities, accelerating the path toward life. There are more speculative forms of panspermia as well. Some suggest that not only molecules but microbes themselves might survive journeys through space. Certain bacteria on Earth are extraordinarily resistant to heat, cold, radiation, and vacuum. Experiments have shown that microbes sealed within rocks could potentially survive the harsh conditions of space for long periods, especially if shielded from direct radiation. If a meteorite was ejected from a planet with life by an impact, it could, in theory, carry microbes across space and deposit them on another world. This version of panspermia raises the possibility that life might travel between planets, perhaps even between star systems, slowly but surely, spreading through the galaxy. Though intriguing, panspermia does not eliminate the question of origins, it only shifts it. If life's building blocks came from comets, where did they form before that? If microbes traveled from another planet, how did they arise there? Panspermia provides a possible mechanism for distribution, but the question of first beginnings remains. Still, the theory widens our perspective. Instead of imagining life as a rare accident confined to Earth, it invites us to see it as a cosmic tendency, a process that may occur wherever conditions permit. There is a calming beauty in this thought. Imagine the universe not as empty and barren, but as filled with seeds, drifting through space, falling onto worlds like gentle rain. Some seeds land on sterile ground and vanish without trace. Others fall onto fertile soil, where they take root and grow. Earth may be one of these fertile places, a planet where seeds from the cosmos found a home. If so, then our lineage stretches beyond this world, connected to the wider fabric of the universe. Every living thing on Earth would be a continuation of a process that began long before our planet was born. This perspective also influences the search for life elsewhere. If the ingredients of life are widespread, then life itself may not be rare. On Mars, ancient riverbeds and lakebeds suggest that water once flowed. If organic molecules were delivered there as well, perhaps life once took hold. On icy moons like Europa and Enceladus, oceans lie hidden beneath thick crusts of ice, warmed by internal heat. These oceans may be rich in organics, carried there by comets, or formed in place. If panspermia is real, then life may have sprouted on many worlds, each one a variation on the same cosmic theme. At the same time, panspermia has its critics. Some argue that while organic molecules can form in space, they are not sufficient by themselves to explain life. Others point out that the survival of microbes across interstellar distances is uncertain, with radiation and time posing formidable obstacles. Still, the evidence that organics are widespread is strong, and whether or not life itself travels between worlds, the idea that Earth was seeded with extraterrestrial ingredients is hard to dismiss. As you rest with these thoughts, imagine the vastness of space. Stars scattered like jewels, clouds of dust and gas glowing in the dark. Within these clouds, molecules form, drifting quietly for millions of years. Comets condense from them, carrying ice and organics. Slowly, silently, they travel until gravity pulls them toward a young planet. They strike its surface, releasing water, minerals, and molecules into its oceans. In this gentle vision, life's story begins not only with Earth, but with the cosmos itself, a story written across the stars. The theory of panspermia may never be proven fully, for the events it describes are hidden in the depths of time and space. Yet its value lies not only in its plausibility, but in its perspective. It reminds us that life is not isolated but part of a larger universe, that the chemistry of living things is connected to the chemistry of the stars. Whether life began on Earth or was seeded from beyond, its roots reach outward, entwined with the wider cosmos. And so, in this part of our journey, we see that life's origins may not be confined to one place or one process. They may be local and cosmic at once, shaped by the Earth but nourished by the stars. In the next part, we will return to the present day, exploring how scientists continue to recreate and investigate these ancient conditions in laboratories, seeking to understand not only how life began, but how it might begin again. 17. Laboratory explorations. Today, as we reflect on the ancient past, it is natural to wonder how we can know anything about events that took place billions of years ago, long before there were fossils, records, or witnesses. The answer lies not only in studying the rocks and the chemistry of Earth itself, but also in recreating early conditions within the laboratory. Scientists today continue to explore the possible pathways from chemistry to biology by building small worlds in glass flasks and controlled chambers, worlds designed to mimic the Earth of long ago. In these spaces, they test theories about primordial soup, hydrothermal vents, and self-replicating molecules. These explorations may not provide definitive answers, but they offer glimpses, possibilities, and guidance, narrowing the gap between speculation and understanding. The work of Miller and Urey in the 1950s was one of the first steps in this direction, demonstrating that amino acids could form from simple gases and sparks of electricity. Since then, countless variations of their experiment have been performed, exploring different mixtures of gases, different sources of energy, and different environments. In some cases, amino acids formed readily. In others, nucleotides and sugars emerged. These results show that the building blocks of life can arise under many conditions, not only one narrow set. Each experiment adds to a growing sense that the chemistry of life is not impossibly rare, but may be a natural outcome of the right environment. Modern laboratories go far beyond these early experiments. Some researchers simulate the environments of hydrothermal vents by creating systems of high pressure and heat, mixing minerals and seawater-like solutions. In these experiments, organic molecules often form along the surfaces of iron and sulfur minerals, suggesting that the vents of the deep ocean could indeed have nurtured life's beginnings. Others recreate shallow pools, cycling them through periods of drying and wetting, to see how nucleotides and lipids might assemble into longer chains or simple membranes. These cycles show that repetition and variation, driven by natural rhythms, could have guided molecules toward greater complexity. One of the most intriguing areas of research focuses on RNA. The RNA world hypothesis suggests that RNA may have been the first molecule capable of both carrying information and performing chemical reactions. Scientists have worked to build RNA molecules that can replicate themselves or help other RNA molecules form. Though complete self-replication has not yet been achieved in the laboratory, progress continues. Ribozymes' RNA molecules with catalytic activity have been engineered to link nucleotides into longer chains, and others can cut and splice RNA sequences. Each success brings us closer to understanding how RNA could have supported the earliest forms of life. In addition to RNA, researchers explore the possibility of alternative molecules. Could life have begun with something simpler than RNA, a precursor molecule that carried information less efficiently but was easier to form? Experiments with molecules, such as peptide nucleic acids and threose nucleic acids, suggest that other systems might have played a role in the transition from chemistry to biology. These molecules can form stable chains and even pair in ways similar to DNA and RNA. It may be that life did not begin with one molecule alone, but passed through a series of stages, each one refining the capacity to store and copy information. Laboratory explorations also extend to protocells, those simple bubbles of lipids that enclose water and molecules. Scientists have created protocells that can grow by absorbing lipids from their surroundings and divide under stress. Some protocells can even encapsulate RNA or other molecules, creating tiny testbeds for interactions. In these experiments, researchers observe how encapsulation changes the behavior of molecules, often stabilizing them and encouraging more complex activity. Such studies show how the emergence of membranes may have supported the leap from free-floating molecules to true cells. Another branch of research looks beyond Earth itself, recreating conditions on other worlds to test whether life's ingredients could form there as well. By simulating the icy surfaces of moons like Europa or Titan, scientists have shown that organic molecules can arise in environments very different from Earth's early oceans. These findings not only broaden our understanding of life's origins here, but also hint at the possibility of life elsewhere, shaped by chemistry that follows similar rules in other corners of the cosmos. These laboratory explorations are not attempts to create life in its fullness. Rather, they are efforts to understand the steps, the transitions, the gradual accumulation of complexity. Each experiment is a window into one part of the process. Some reveal how molecules form, others how they link, still others how they persist or replicate. By combining these insights, scientists weave together a narrative of life's beginnings, one that is not fixed but flexible, open to refinement as new discoveries are made. It is soothing to think of these laboratories not as places of artificiality but as echoes of nature's own experiments. On the early Earth, countless reactions played out in oceans, vents, and pools. Today, scientists condense those reactions into flasks and chambers, repeating them under careful observation. The patience of nature is mirrored in the patience of researchers, each experiment a small step in the same long journey. The glass vessels, filled with gases, minerals, and water, are like miniature Earths, reminders that life is a process of chemistry, unfolding wherever conditions allow. These explorations also remind us of the humility of science. No single experiment has recreated life from non-life. No laboratory has yet produced a living cell from scratch. But the work continues, not with urgency, but with steady persistence. Each discovery adds a piece to the puzzle, clarifying how simple molecules could assemble into systems with the qualities of life. It is not the sudden leap that matters, but the accumulation of small insights, the gradual illumination of a process that took billions of years to unfold. As you imagine these laboratories, think of them not as sterile or mechanical, but as quiet spaces where ancient mysteries are revisited. Picture a flask filled with a mist of gases, sparks flashing within it, droplets condensing on the glass. Picture a chamber filled with hot water and minerals, steam rising as new molecules form. Picture a droplet of water under a microscope, where lipid bubbles dance and divide. In these small scenes, we glimpse echoes of the early Earth, recreated with care to answer questions as old as humanity itself. And so, laboratory explorations today are not merely scientific exercises. They are acts of curiosity and continuity, efforts to reconnect with the deepest roots of life. They remind us that the story of our existence is not closed but open, still being uncovered, still being tested and refined. Each experiment is a bridge between past and present, between the ancient Earth and the modern world, between chemistry and biology. As this part of our journey comes to rest, we may hold the thought that the quest to understand life's origins is itself a reflection of life, persistent, adaptive, and ever-evolving. Just as molecules once explored countless combinations until life emerged, so too do scientists explore countless experiments, seeking to glimpse the same unfolding. In the next part, we will step back to see the unity of all living things, how the shared genetic code ties together bacteria, plants, animals, and humans, pointing to a common ancestor that links all of life's diverse forms. 18. The unity of all living things. As we draw closer to the present in our journey through life's origins, it becomes clear that despite the diversity of organisms that cover the earth today, there is an underlying unity that ties them all together. Every tree in the forest, every fish in the sea, every bird in the sky, and every human being shares a common ancestry, a thread of continuity that stretches back to the first microbes. This unity is written in the language of life itself, in the molecules that form our bodies, in the codes that guide our growth, and in the processes that sustain us. To reflect on this unity is to see life not as a collection of separate beings, but as one vast, interconnected family, diverse in form but singular in origin. At the center of this unity lies the genetic code, the system by which information is stored and expressed in every living cell. DNA, composed of long chains of nucleotides, holds the instructions for building proteins. The code is universal. The same sequences of 3 nucleotides, called codons, specify the same amino acids across all known organisms. A bacterium, a plant, and a human all read the code in the same way. This universality is one of the strongest pieces of evidence that all life descends from a common ancestor. It suggests that once the code was established, early in life's history, it was passed down faithfully, conserved through billions of years of evolution. Beyond the code itself, the machinery of life is also shared. All cells use ribosomes, complex assemblies of RNA and protein, to build proteins according to the genetic instructions. All cells rely on ATP, a small molecule, as their primary carrier of energy. All cells are enclosed by membranes made of lipids, and all cells replicate by copying their DNA or RNA and dividing into 2. These commonalities are so consistent that they can only be explained by shared descent. It is as though all life speaks the same ancient language, with accents and variations, but with grammar and vocabulary unchanged across the ages. The unity of life is also evident in the evolutionary patterns that link organisms together. When scientists compare the DNA sequences of different species, they find similarities that mirror the branching patterns of descent. Humans share more DNA with chimpanzees than with dogs, more with dogs than with fish, more with fish than with plants. But some similarities exist across all. Certain genes are so fundamental that they are nearly identical in bacteria and in humans, unchanged because they perform essential roles that cannot be altered without disrupting life itself. These conserved genes act as living fossils, reminders of the deep connections that bind all organisms. It is soothing to think that within each of us lies a record of this shared history. Our DNA carries not only the instructions for our own bodies, but echoes of our ancestors stretching back to the first cells. The same molecules that allow us to breathe, to move, and to think are built with the same code that guided the earliest microbes. We are, in a very real sense, extensions of that ancient life, its descendants, carrying forward the patterns it first established. Every heartbeat, every breath, every cell division is a continuation of processes billions of years old. The unity of life extends beyond biology into the very materials of our bodies. The atoms that make us carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur are the same atoms that circulate through plants, animals, and microbes. They are recycled endlessly, moving through air, water, soil, and living beings in cycles that connect us all. The oxygen we inhale was produced by photosynthetic organisms. The carbon in our bones may once have been part of a leaf. The water in our blood may have flowed in rivers millions of years ago. In this way, unity is not only genetic but elemental. Life shares not only a code but a common pool of matter, a continuous exchange that binds us to all other beings. The recognition of life's unity also brings humility. Though humans have developed consciousness and culture, though we build cities and ponder the stars, We remain part of the same lineage as the simplest microbe. The differences are matters of degree and complexity, not of fundamental nature. The processes that allow us to think are built upon the same molecular foundations that allow bacteria to divide. To see this clearly is to be reminded of our place in the web of life. Not above it, but within it, one branch among many on a single vast tree. This tree of life is more than a metaphor. Scientists have mapped it by comparing genetic sequences across organisms, building a picture of how species are related through time. At its root lies the last universal common ancestor, a cell or community of cells that lived more than 3 billion years ago. From this ancestor, all known life descends. Its features can be inferred from what is shared among all living things: a genetic code, a reliance on RNA and proteins, a metabolism powered by chemical gradients, and a membrane to enclose it all. Though the details are uncertain, the existence of such an ancestor is almost undeniable, for unity demands a beginning point from which diversity spread. It is calming to imagine this ancestor not as a single remarkable cell, but as a population, a community of simple organisms exchanging genes and sharing innovations. From this community, lineages branched and diversified, some giving rise to bacteria, others to archaea, and still others to the eukaryotes that would one day include plants and animals. The tree of life grew not from a single trunk, but from a braided root, a mingling of lineages that over time became distinct. This vision emphasizes that unity does not mean uniformity, but shared origin, a foundation upon which endless variety could flourish. The unity of life has profound implications for how we view ourselves and our world. It means that when we study a bacterium, we learn not only about microbes, but about processes that also occur in our own cells. It means that medical discoveries, agricultural advances, and environmental understanding are all interconnected, grounded in the same biology. It means that the health of ecosystems, the balance of climate, and the survival of species are bound to our own fate, for we are part of the same living fabric. As you rest with these reflections, imagine life not as a collection of separate beings, but as one great organism, expressed in many forms. Imagine the tree of life, its roots deep in the past, its branches spreading into the present, each leaf a species, each twig a lineage, all connected. We are leaves on this tree, no more and no less, sustained by the same trunk, shaped by the same roots. The unity of all living things is not an abstraction, but a reality, written in our DNA, carried in our breath, and reflected in every cell. And so, in this part of our journey, we see that diversity and unity are not opposites but companions. Life is endlessly varied, yet all variations are bound by a common thread. The smallest bacterium and the largest whale, the simplest moss and the tallest tree, all are kin. All share a heritage that stretches back to the dawn of life. In the next part, we will reflect on life's fragile first steps, considering how improbable those beginnings may have seemed, and how remarkable it is that they endured to give rise to the living world we know today. 19. Life's fragile first steps. As we look back across the immense span of time that separates us from the dawn of life, it is easy to imagine that life's emergence was inevitable, that once the right ingredients and conditions were present, the path toward biology was clear. Yet when we pause to reflect more gently, we can see how delicate those first steps must have been. Life's beginnings were not a single moment, but a fragile unfolding, a series of transitions that could easily have faltered. Molecules had to assemble, persist, and replicate, despite constant threats from heat, radiation, impacts from space, and the chaos of an unsettled planet. Each step was precarious, each advance balanced on the edge between persistence and dissolution. That life endured at all, and not only endured but flourished, is one of the quiet marvels of Earth's history. The earliest molecules that hinted at life were fragile by nature. Chains of nucleotides could break apart in water or under ultraviolet light. Lipid bubbles could collapse or rupture with changes in temperature. Replicating strands could copy themselves imperfectly and lose stability. Without protection or enclosure, most molecules would have dissolved back into the ocean, their brief existence forgotten. And yet, some endured. Perhaps they found shelter in mineral pores or within the walls of protocells. Perhaps cycles of wetting and drying concentrated them enough to persist. In these small refuges, fragile molecules gained time, and time was the most precious resource of all. The early Earth was not always kind to life's first attempts. Meteorites and comets bombarded the surface, releasing heat and energy that could vaporize oceans or sterilize regions. Volcanoes erupted, filling the air with ash and gases. Lightning split the skies, and radiation from the sun struck the surface without the protection of an ozone layer. Any one of these forces could disrupt fragile chemistry, breaking apart molecules before they had a chance to grow. Yet the Earth was vast, and its environments varied. Even if life's early experiments were wiped away in one place, they may have continued elsewhere, sheltered in the depths of the oceans or in quiet pools, untouched by catastrophe. This resilience was not in the strength of molecules themselves, but in the sheer patience of nature, repeating experiments endlessly until something endured. The transition from chemistry to biology was not a single leap, but a series of fragile steps. Molecules had to form. They had to link into chains. They had to develop the ability to copy themselves. They had to find protection within protocells. They had to establish basic metabolisms. Each of these steps was improbable, each dependent on countless small interactions. And yet, improbability is softened by time. Over millions of years, with countless molecules and endless cycles of reaction, even the rarest events become likely. Fragility, when given enough time, can lead to persistence. It is soothing to think of life's beginnings not as a sudden miracle, but as a gentle process, unfolding slowly, patiently, almost tentatively. Imagine the oceans of early Earth, filled with molecules drifting, colliding, and parting. Most encounters lead to nothing. Chains form and dissolve. Bubbles rise and burst. Patterns appear and vanish. Yet now and then, a molecule forms that is just stable enough to last a little longer, just effective enough to copy itself, just fortunate enough to be enclosed within a vesicle. These small successes accumulate, and over time, they begin to shape the direction of chemistry. What was once random becomes structured. What was fragile becomes enduring. The fragility of life's beginnings also reminds us of its rarity. While the ingredients of life may be common: water, carbon, energy, the path to true biology requires a sequence of delicate steps, each one building upon the last. If any step had faltered completely, life might never have taken hold. Earth might have remained barren, a planet of oceans and rocks, without the richness we now see. The fact that life emerged here suggests that fragility does not mean impossibility, but it also cautions us against assuming that life must be abundant everywhere. It may be that the cosmos is filled with the ingredients of life, but that the fragile sequence of steps needed to create living systems succeeds only rarely. And yet, fragility can also be a source of strength. Once life's first systems endured, they began to evolve, and evolution is itself a response to fragility. Replication with variation allows adaptation, and adaptation allows survival in changing conditions. Life, born fragile, became resilient by evolving. Each challenge, each threat, shaped it into forms better suited to endure. The fragility of the beginning gave rise to the strength of continuation. From delicate molecules emerged cells, from cells communities, from communities ecosystems. What began as precarious has become persistent, enduring across billions of years and countless changes. The fragility of life's first steps is mirrored in our own experience of life today. Each of us begins as a single cell, delicate and dependent, yet from that fragility grows an entire organism. The processes that sustain us, breathing, metabolism, reproduction, are all continuations of those earliest systems. The fragility of beginnings is not unique to the past. It is part of life's nature, a reminder that strength is built from delicacy, persistence from vulnerability. As you rest with these thoughts, imagine the young earth as a place of constant motion and change. The seas shimmer under a hazy sky, their surfaces broken by waves and storms. Within them, molecules drift, most fragile, most fleeting, but some enduring. Tiny bubbles enclose fragile chemistries. Replicating strands lengthen and divide. The first protocells wobble in the currents, dividing unevenly, carrying with them the promise of persistence. They are fragile, easily destroyed, but they are also resilient in their numbers and in the patience of time. Out of this fragility, life begins to take root, quietly and without fanfare. It is humbling to think that everything we see today, forests, oceans, animals, and ourselves, depends on those fragile first steps. Without them, Earth would be silent, its seas lifeless, its skies empty of birds, its lands barren of trees. All the beauty and diversity of the living world is built on the persistence of delicate molecules, sheltered and nurtured across ages until they could sustain themselves. Fragility, in this sense, is not a weakness but a doorway, the threshold through which life passed to become what it is today. And so, in this part of the journey, we pause with gratitude for the fragility of life's first steps, for the delicate experiments of chemistry that, against all odds, endured. They remind us that life is not only strong but also tender, that endurance often arises from vulnerability, and that even the smallest beginnings can give rise to the grandest continuations. In the next and final part, we will draw our reflections together, considering the mystery that still surrounds life's origins and the gentle wonder that such a story inspires as we drift toward rest. 20. Closing reflections. As our journey through the origins of life comes to its quiet conclusion, we are left with a story that is vast in scope yet gentle in its unfolding. From the fiery beginnings of Earth, when the planet was still cooling and shaping itself, to the first fragile molecules drifting in the oceans, to the rise of replicating strands, protocells, microbes, and finally, the transformation of the planet itself through photosynthesis and oxygen, we have traced a path that is both intricate and serene. Life did not emerge suddenly or dramatically, but grew slowly out of chemistry, nurtured by water, minerals, and energy, guided by the patience of time. It is a story still incomplete, still filled with mystery, yet it offers us a soothing reminder that even the most extraordinary things can arise from the simplest beginnings. When we reflect on all the steps that life required to take the formation of organic molecules, the emergence of replication, the creation of protective enclosures, the unity of genetic codes, and the shaping of Earth's atmosphere, it is humbling to realize how improbable each step seems when viewed in isolation. And yet, improbability softens when stretched across billions of years. Time is the patient canvas upon which these delicate processes painted themselves, repeating endlessly, exploring every possibility until persistence was found. In this way, life's origins remind us that persistence and patience can transform fragility into resilience, and small beginnings into grand continuations. There is also wonder in recognizing that the story of life is not only about Earth but also about the wider cosmos. The molecules that form the basis of life may have been forged in the hearts of stars, carried across space in comets and meteorites, delivered to Earth as gifts from the universe. Whether life arose here entirely from local chemistry or was seeded in part from beyond, We are deeply connected to the cosmos. The carbon in our bodies was once part of ancient stars. The water we drink may have arrived on comets, and the oxygen we breathe was shaped by microbial life billions of years ago. Our story is not separate from the universe, it is an extension of it. The closing reflections on life's origins also remind us of unity. For all the diversity of living beings, from bacteria to whales, from mosses to humans, there is a single lineage that binds us all together. The same genetic code runs through every cell. The same processes of metabolism and replication sustain us all. The same molecules build our bodies and flow through our veins. To know this is to see life not as a collection of separate entities, but as one vast organism expressed in countless forms. This unity is a source of comfort, for it means that we are never truly alone. We are part of a vast and ancient family that began billions of years ago, with fragile molecules in quiet oceans. There are still mysteries that science has not yet answered. We do not know exactly how the first replicating systems arose, or whether life began in tidal pools, hydrothermal vents, or somewhere entirely different. We do not know if life is unique to Earth or if it thrives elsewhere in the universe, hidden beneath icy crusts or orbiting distant stars. These mysteries are not failures but invitations, reminders that knowledge is always unfolding, that curiosity is endless, and that life itself is a process of discovery. In this way, the unknown is not troubling but calming, for it leaves room for wonder and reflection. It is soothing to think of life's beginnings not as a solitary event long past, but as a process that continues even now. Every cell division, every replication of DNA, every cycle of metabolism is a reenactment of ancient processes. The rhythms of life did not begin and end billions of years ago. They are ongoing, repeated in every living being. We are continuations of the first cells, carrying forward the same patterns, shaped by the same forces, sustained by the same chemistry. To live is to participate in that ancient continuity, to be part of the same story that began in quiet waters long ago. As we bring this journey to rest, let us imagine once more the early Earth. The skies are hazy with volcanic gases, the oceans warm and rich with molecules, the land still barren. Within shallow pools and along the deep sea floor, fragile bubbles drift, enclosing strands of RNA. Lightning flashes above, hydrothermal vents glow below. And in these places, chemistry begins to resemble biology. Slowly, protocells divide, microbes thrive, oxygen fills the skies, and life reshapes the planet. From these quiet beginnings, all the richness of today flows the forests, the rivers, the animals, and ourselves. The story stretches from then until now, unbroken, continuous, patient. There is comfort in knowing that our own lives, brief as they are part of this greater continuity. We are not separate from life's origins, but participants in them. The air we breathe connects us to cyanobacteria of billions of years ago. The water in our bodies connects us to ancient oceans. The atoms within us connect us to stars, long vanished. Every living being carries within it echoes of the first steps of life, reminders that fragility can give rise to strength, and that persistence can create beauty. As you rest with these reflections, allow yourself to imagine drifting gently in that ancient ocean, carried by currents, surrounded by invisible life. The molecules and cells around you are fragile, but they endure. They are patient, repeating their cycles again and again, until at last they form the foundation of all that is to come. From such a scene, the world we know is born. From such fragility, strength emerges. From such simplicity, complexity unfolds. And so we close this journey, not with finality, but with calm acceptance of mystery and wonder. Life's origins remain partly hidden, but enough has been revealed for us to see the outlines of the story. A planet once barren, slowly becoming alive. Molecules once fleeting, slowly becoming enduring. Fragile beginnings, slowly becoming resilient continuations. It is a story written in chemistry, in patience, in time itself. It is our story, shared by every living being, bound together by the same ancient thread. As you let these thoughts settle, remember that the origins of life are not only a scientific question, but also a source of peace. They remind us that from the smallest beginnings, great things can grow, that fragility need not prevent endurance, and that we are part of something vast, ancient, and beautiful. In this way, the mystery of life's origins is not only about the past, but about the present, about the quiet miracle of existence itself, unfolding moment by moment, breath by breath, heartbeat by heartbeat.